Geological catastrophes represent moments when the planet, like a colossal mechanism, experiences destructive events that ultimately lead to the creation of new landscapes and ecosystems. These catastrophes, including earthquakes, volcanic eruptions, or floods, occur against the backdrop of the majestic tranquility that prevails in geological time. Earth, with its multi-billion-year history, experiences such events as moments that, although they may seem catastrophic from a human perspective, are natural processes embedded in the planet's rhythm. For example, in the last 60 million years, more than 100 major volcanic eruptions have occurred on Earth, each leaving its mark in the geological layer. These eruptions have formed new mountain ranges such as the Andes and created fertile soils that later became the basis for agriculture. The age of Earth is approximately 4.5 billion years, and during this time it has experienced numerous cycles of mountain building and erosion, demonstrating how catastrophic events can contribute to long-term geological changes. When an earthquake occurs, such as the one in Chile in 1960, which was one of the most powerful in history, with a magnitude of 9.5, it not only destroys but also creates new geological structures such as faults and depressions. This reminds us that even destruction carries the potential for new life. Approximately 80% of all volcanic activity on Earth is concentrated on the ocean floor, where underwater volcanoes form new islands and alter marine ecosystems. Over millions of years, such events lead to the formation of new geological formations, such as reefs, which become homes for diverse marine organisms. Periods of calm between catastrophes can last for millions of years, during which Earth may seem static, and life on it thrives in its forms, as it did during the Jurassic period when dinosaurs dominated the planet. However, when we look at the entire history of Earth, it is clear that these calm periods are always interrupted by sudden and powerful catastrophes that remind us of its dynamic nature. For example, more than 300 million years ago, at the end of the Permian period, a mass extinction occurred, resulting in the disappearance of around 95% of all species on the planet. This catastrophe, although it caused enormous losses, also paved the way for the evolution of new creatures, including dinosaurs and mammals. It is important to understand that geological catastrophes are not random events. They are part of long-term processes that shape the appearance of our planet. Every mountain range, every depression, and every lake were formed as a result of numerous such events that have occurred over millions of years. For example, the height of Mount Everest, which is currently 8,848 meters, is the result of the collision of the Indian and Eurasian tectonic plates, which began more than 60 million years ago and continues to this day. Thus, geological catastrophes become an integral part of Earth's history, where each destruction is a preamble to the creation of something new. From a geological perspective, such catastrophes are not just destructive events, but important moments of change that become the foundation for future biodiversity. Formed more than 4.5 billion years ago, Earth was born into the harsh chaos of the cosmos. Initially, this planet was a molten sphere of rocks and gases, emerging from a vast cloud of hydrogen, helium, and heavy elements created by stellar explosions. Over millions of years, particles orbiting the newly formed Sun gradually coalesced, forming larger bodies known as planetesimals. These planetesimals, ranging in size from several meters to hundreds of kilometers, collided with immense force, generating enormous heat. Temperatures on the surfaces of these bodies reached thousands of degrees Celsius, creating conditions for partial melting and the release of lighter gases such as water vapor and carbon dioxide. Collisions were ubiquitous. Catastrophic impacts occurred every few thousand years, continually increasing the mass of the future planet. Around 4 billion years ago, Earth had gained sufficient mass to retain an atmosphere composed mainly of water vapor, methane, and ammonia. This primary atmospheric cocktail was a result of volcanic activity and the release of gases from molten rocks. While some parts of the planet continued to cool, others remained hot, and in these conditions, oceans began to form. The surface of Earth was constantly changing. Molten landscapes filled with lava, flows of magma, and smoking volcanoes created a unique atmosphere of primeval chaos. The formation of continents had not yet begun, and the entire planet was one vast ocean of molten magma, where each drop could serve as the foundation for future forms of life. The process of Earth's formation was not just physical, but also chemical. Under extreme pressure and temperature, reactions occurred that later led to the formation of complex molecules. Over hundreds of millions of years, this chaos gradually transformed into order, but in its early stages, it pulsed with the ominous energy of destructive collisions. It was from this cosmic madness, these volcanic storms and catastrophes, that the conditions for life eventually emerged. Around the newly formed planet, a belt of debris and dust formed, which acted as a magnet for new particles, continuing to approach and coalesce with the existing mass. This process lasted about 100 million years until Earth finally took its shape. Eventually, the temperature dropped to a level where water could exist in liquid form, marking a crucial stage for the emergence of the first life. The formation of Earth's primary crust began approximately 100 million years after its creation, when the molten surface gradually cooled, creating a thin, solid shell capable of withstanding the planet's internal forces. At that time, the surface temperature exceeded 1,000 degrees Celsius, and magma erupting onto the surface formed vast lava fields. This process lasted for millions of years until the temperature dropped to around 800 degrees Celsius, allowing primary minerals such as olivine and pyroxene to form. The primary crust was very fragile, prone to cracking and breaking under the high temperatures and pressure generated by magma flows rising from the planet's interior. This crust had low strength and could easily be destroyed when internal forces pushed magma, creating new rifts and craters. During this period, Earth's surface gradually sank into darkness as the cooling crust no longer glowed with the incandescent light of its molten state, becoming dark and smooth. At this stage, the first continents emerged. Lighter rock formations rose above the ocean level, laying the foundation for future land masses. Around 300 million years after the crust's formation, the first oceans began to form as water vapor clouds condensed, filling the depressions. These primary oceans played a critical role in the development of life, providing conditions for the emergence of the first simple organisms. Scientific research conducted in recent decades has shown that it was during this period, approximately 3 billion years ago, that the first microscopic organisms began to form on Earth, serving as the foundation for the evolution of all known forms of life. Approximately 4.5 billion years ago, during the period when our planet was just beginning to form, Proto-Earth collided with a mysterious planet the size of Mars, known as Theia. These two celestial bodies, moving along their orbits, slowly approached each other, like two dancers performing a complex and majestic choreographic number in the void of space. Research shows that Proto-Earth had a diameter of about 12,000 kilometers, while Theia was slightly smaller, with a diameter of approximately 9,000 kilometers. This collision, occurring at a speed of around 10 kilometers per second, was one of the most catastrophic events in the history of our planet. Upon impact, a giant cloud of molten and gaseous materials was ejected into space, forming a temporary ring around Proto-Earth. A torrent of debris consisting of rock and metallic iron rushed in all directions, creating unimaginable flows of matter that could eclipse all known human disasters. Over time, over the course of several tens of thousands of years, these debris began to coalesce, forming the Moon. The formation of the Moon took between 30 to 100 million years, and during this period, it was significantly closer to Earth than it is now. Research conducted by NASA and other space agencies shows that the Moon, formed from the ejected material, initially had much more active volcanic activity. This activity was due to the heat released as a result of the collision continuing to heat the young Moon. For example, enormous basaltic plains were formed, which later became known as the seas of the Moon, such as the Sea of Tranquility and the Sea of Showers. Lunar seas represent vast plateaus covered with basaltic rocks, which, in turn, were formed from lava that flowed onto the surface billions of years ago. This process of collision and subsequent moon formation had a significant impact on the stability of Earth's rotation, as well as on its climate and other conditions necessary for the emergence of life. As a result of this colossal catastrophe, conditions were created for the formation of the atmosphere, as well as for the appearance of the first bodies of water on Earth, which became the basis for further life development. As the Moon moved away from Earth, its orbit stabilized the tilt of our planet's axis, which in turn influenced the change of seasons. Thus, the collision of proto-Earth with Theia not only created the satellite we see today, but also formed the conditions necessary for the development of life on Earth. As a result of this collision, a multitude of unique geological and atmospheric phenomena emerged, which continue to be studied by scientists to this day. After the collision of proto-Earth with Theia on the orbit of our planet, particles began to form, ejected as a result of the catastrophic impact. These particles, composed of melted and scattered fragments of the crust and mantle of both bodies, gradually began to coalesce into a single whole. Over the first few 100,000 years after the collision, due to gravitational interactions, these debris began to unite into larger bodies, forming a proto-lunar. This process occurred under conditions where the temperature on the orbit was extremely high, and particles collided with each other, merging and forming more massive clumps. Around 4.5 billion years ago, when Earth was still young and turbulent, this process of convergence and accumulation reached its peak. Proto-lunar, growing in size, began to acquire its own gravity, which further attracted the surrounding particles. These particles accumulated on its surface, creating a primary crust of magma. As the material cooled, craters and volcanic formations began to form on the Moon, leaving traces of their existence on the surface. Around 100 million years later, when proto-lunar completed its growth, it became a full-fledged satellite of Earth, located at a distance of approximately 380,000 kilometers. This new satellite had a significant impact on Earth, beginning to regulate tides and ebbs, which contributed to the formation of ecosystems on the planet. Lunar tides caused by gravitational interaction began to change the level of the oceans, creating unique conditions for the emergence of life. In addition, the Moon stabilized the axis of rotation of Earth, providing more predictable climatic conditions. The satellite continues to influence the rotation speed of our planet, slowing it down by several milliseconds per century. Although this process is not noticeable in the short term, over time it accumulates significant changes. Today, the Moon remains a faithful companion of Earth, and its influence, including the creation of tides, continues to shape life on the planet. It has not only become an object of research, but also a source of inspiration for numerous cultures throughout human history. The period of late heavy bombardment of Earth, which occurred several billion years ago, was characterized by intense impacts of asteroids and comets, leading to significant changes on its surface. At that time, the young planet was a true battlefield, where each impact of a celestial body was not only destructive, but also created new forms of relief. Catastrophic collisions occurred on Earth's surface, forming enormous craters and ejecting dust and debris into the atmosphere, causing temporary climate changes. These impacts altered the landscape, forming mountain ranges, valleys, and plains. Each new impact could have the power of millions of tons of TNT, leading to the formation of new minerals and rock types, as high temperatures and pressures caused chemical reactions previously unseen on Earth. Impacts also contributed to the formation of the first oceans, as steam condensed and created water masses. As a result, conditions conducive to the emergence of life were established on the planet. Impacts of comets containing water and organic compounds could introduce the necessary elements for the initiation of biochemical processes. Over millions of years, this bombardment created unique geological formations, such as plateaus and craters, which became the basis for future ecosystems. The young Earth was surrounded by clouds of gas and dust, creating conditions where sunlight barely reached the surface, also affecting climate and temperature. This era was a time of continuous transformation, where each second could mark the beginning of something new. As the planet, like an artist, drew its new features under the influence of cosmic collisions. Such events continued for about 100 million years, creating unimaginable changes in the structure of Earth. Modern research shows that it was during this period that the conditions were formed, which later became the basis for the existence of life on the planet. The formation of the first continents occurred due to these impacts as Earth masses were raised and joined, creating high mountain systems. This geological activity was an integral part of the formation of the planetary structure, shaping what we see today. Impacts occurring in an instant changed the climate, introducing new gases into the atmosphere, such as carbon dioxide and water vapor, which played a key role in the formation of the first oceans. Each impact was not just destruction, but the beginning of a new process that over time led to the formation of ecosystems that we know today. It was during this time that Earth laid its foundations, which later led to the emergence of diverse flora and fauna. Studying these processes allows us to understand how the planet evolved and adapted to changing conditions, and opens new horizons for understanding its geological history. There are theories that it was during this period that Earth received a significant amount of water necessary for life, which is confirmed by the analysis of ancient minerals and fossils. Each collision that occurred on Earth was part of this massive process, which ultimately led to the creation of diverse ecosystems that supported the development of life on the planet. The atmosphere of the earliest Earth was completely unlike what we observe today. It consisted mainly of heavy gases such as methane, ammonia, carbon dioxide, and water vapor, but it contained almost no oxygen. Scientific research indicates that at that time, the oxygen content in the atmosphere was less than 1%, while for life as we know it, this level should be around 21%. The sky on Earth of those days was tinted with reddish hues, which is explained by the presence of iron oxides and other chemical compounds that reflected light in their own way. Phenomena such as electrical discharges, including lightning, pierced this atmosphere, creating a striking but threatening spectacle. These discharges, according to theory, could have served as catalysts for primary chemical reactions that later became the basis for the formation of organic compounds. The surface temperature fluctuated between 100 and 120 degrees Celsius, creating a hellish environment where conditions for life were truly extreme. Massive volcanoes spewed toxic gases, and on the surface of the Earth, frequent catastrophic events such as meteorite impacts occurred, which could have destroyed entire ecosystems that had not yet formed. Scientific models show that during this period, Earth was constantly subjected to cosmic factors such as ultraviolet rays and cosmic rays, leading to the formation of new chemical compounds necessary for the emergence of life. Despite all this hostility, it was in such an atmosphere that the first organic molecules began to form, which became the basis for further evolutionary development. These first steps towards life occurred in conditions where there were many factors that could have made it impossible. Approximately 3.5 billion years ago, in such conditions, the first simplest organisms appeared, which may have been anaerobic bacteria capable of surviving without oxygen. These organisms began the process of photosynthesis, which ultimately changed the composition of the atmosphere, increasing the level of oxygen and creating conditions for more complex forms of life. It is remarkable that the foundations of future ecosystems capable of surviving in conditions that we now consider normal emerged in such a hostile environment. Primary oceans began to form approximately 3.5 billion years ago when comets and asteroids rich in water struck Earth. These celestial bodies, composed of ice and minerals, accumulated water in the planet's low-lying areas, gradually filling depressions and forming vast bodies of water. The composition of this primary water was rich in minerals such as sodium, calcium, magnesium, and sulfates, creating ideal conditions for the emergence of the first biochemical processes. The color of the oceans at that time varied from blue to greenish due to the high concentration of dissolved substances and organic compounds such as iron and hydrogen sulfide, which gave the water its characteristic hue. This mineralization ensured an alkaline environment, which facilitated the chemical reactions necessary for the formation of simple organic molecules. The volume of the primary oceans, according to some estimates, reached around 70% of Earth's surface, creating conditions similar to modern deep seas, where water temperature fluctuated between 20 and 30 degrees Celsius. These primary water bodies were not just empty basins, they became catalysts for the chemical reactions necessary for the formation of amino acids and other organic compounds. Over millions of years, the water in these oceans underwent constant changes under the influence of solar radiation, volcanic activity, and other geological processes, leading to the formation of complex ecosystems that later became the basis for the emergence of multicellular life. Scientific research indicates that during this period, active processes of photosynthesis occurred, not only due to plants, but also due to primitive bacteria that used sunlight to synthesize organic substances. These microorganisms, such as cyanobacteria, began to release oxygen into the ocean, which in turn altered the chemical composition of the water and contributed to the emergence of more complex forms of life. Such changes in the oceans also served as catalysts for the formation of the first continents, as minerals settling on the bottom formed solid rocks. Ocean water, enriched with carbon and other chemical elements, created conditions for the biosphere, which subsequently led to the mass evolution of living organisms. The water of the primary oceans became not just a habitat, but also the cradle of life, where the first ecosystems emerged, which later changed the face of Earth. Primary oceans contained more than 30 chemical elements necessary for life, including carbon, oxygen, hydrogen, nitrogen, and phosphorus, highlighting their role in the formation of biochemical cycles that remain relevant to this day. The Earth's crust is divided into mobile segments that slowly drift across the planet's surface, forming a system known as plate tectonics. This concept was first proposed in the early 20th century when geologists began to realize that continents are not static, but move over time. Plate tectonics is based on the idea that the Earth's crust consists of several large and small plates that float on a more viscous layer of mantle material beneath them. This layer, known as the asthenosphere, can flow, allowing the plates to move at a speed comparable to the growth of human fingernails, from several millimeters to several centimeters per year. The movement of plates leads to the formation of mountain ranges, oceanic trenches, and earthquakes. For example, as plates collide, they create powerful mountain systems, such as the Himalayas, which continue to grow even today. Meanwhile, some plates collide and rise while others subduct, creating zones of subduction where Earth materials are recycled. This process not only changes the surface topography, but also influences climate, ecosystems, and even life on Earth. In the long term, plate tectonics ensures the continuous renewal and redistribution of the planet's resources. For instance, volcanism caused by plate movement creates new islands and alters the composition of the atmosphere, significantly contributing to climate formation. It is also important to note that major tectonic events occur unevenly with intervals of millions of years, making Earth's history truly dynamic and complex. Plate tectonics is not just a theory, but a fundamental principle that explains many geological and climatic processes occurring on the planet. Indeed, this activity has been ongoing for billions of years, and only in the last millions of years has humanity begun to witness the consequences of this relentless movement. Subduction is a process in which one tectonic plate slowly descends beneath another, returning to the Earth's mantle. This mechanism is observed in subduction zones, where an oceanic plate collides with a continental plate, resulting in the formation of deep oceanic trenches and mountain ranges. The most well-known example is the subduction zone along the Pacific Ring of Fire, where the Pacific Plate is subducting beneath the North American Plate. This process occurs over millions of years, creating tension between the plates that accumulates due to their constant movement. Pressure at the plate boundaries can build up until there is a sudden release of energy, causing an earthquake. For instance, the magnitude 9 earthquake that occurred in Japan in 2011 was caused by this mechanism. It was one of the most powerful earthquakes ever recorded, clearly demonstrating the power of the processes occurring beneath our planet. In subduction zones, volcanic eruptions are also common, resulting from the melting of the subducting plate. As the oceanic plate descends into the mantle, it heats up and deforms, leading to the formation of magma. This magma rises to the surface, causing volcanic eruptions such as Mount Fuji in Japan, which is located near active subduction zones. Subduction not only shapes the landscape but also influences climate conditions, as volcanic eruptions can release large amounts of ash and gases into the atmosphere, altering temperature. For example, the eruption of Krakatoa in 1883 caused a significant drop in global temperature, affecting crop yields and climate conditions. Subduction is a complex and multifaceted process that continues to influence Earth, shaping not only geographical features but also climate conditions and ecosystems that depend on the stability of the landscape. As a result, new lands and dangerous zones form at the plate boundaries, requiring constant monitoring by scientists and seismologists. Scientific research shows that tension in these zones can accumulate over decades or even centuries before a catastrophic event occurs. In this context, understanding the mechanisms of subduction is crucial for predicting earthquakes and volcanic activity, which is vital for the safety of populations living in these regions. According to scientists, approximately 70% of all earthquakes occur in subduction zones. Spreading of the oceanic floor is a process that occurs at the boundaries of tectonic plates, where magma rises from the mantle through faults, creating new oceanic crust. This volcanic process is active in places like the Mid-Atlantic Ridge, which stretches over 16,000 kilometers, starting from the Arctic Ocean and reaching the southern pole. At a depth of about 2.5 to 5 kilometers below the water surface, in complete darkness, molten magma forces its way through cracks in the crust, forming basaltic rocks. The high temperature of the magma reaches around 1200 degrees Celsius, allowing it to melt and rise to the surface. When this magma reaches the surface, it quickly cools, forming new crust that then begins to spread apart neighboring land areas. This process happens continuously, resulting in the formation of new ocean floor at a rate of about 2 centimeters per year. Over millions of years, this can lead to significant geographical changes. For example, a study conducted in 2018 by scientists from Brown University showed that over the past 30 million years, the Atlantic Ocean has expanded by around 30,000 kilometers thanks to the spreading of the oceanic floor. Underwater volcanism at these plate boundaries also leads to the formation of underwater volcanoes that can reach heights of up to 2,000 meters, such as the Sipadan volcano in Indonesia. These volcanoes sometimes erupt lava and volcanic gases into the ocean, creating new ecosystems that develop rapidly around these sources. Interestingly, life on such volcanoes is typically based on chemosynthetic bacteria that use chemical reactions to obtain energy, allowing ecosystems to exist independently of sunlight. The process of oceanic floor spreading not only creates new crustal areas but also affects Earth's climate, as volcanic activity can release significant amounts of carbon dioxide and other greenhouse gases into the atmosphere. Therefore, the ocean floor continues to evolve, and new areas of the Earth's surface are formed as a result of this remarkable underwater process. Supercontinents are massive landmasses composed of all or most of the continents that periodically unite and separate over millions of years. This process is known as the supercontinent cycle and occurs due to tectonic activity, when the plates of the Earth's crust move, collide, and drift apart. Over the past 200 million years, Earth has experienced several such cycles, and it is worth noting that we are currently in a phase where continents such as Asia, Africa, and America are gradually moving closer to each other. This process of land unification affects the climate conditions on the planet as large masses of land alter atmospheric and oceanic currents. For example, when continents come together to form a supercontinent, it can lead to the formation of large mountain systems, which in turn change patterns of rainfall and temperature. Mountain ranges create barriers for winds, which can result in the formation of deserts on one side and wet tropics on the other. These climate changes impact the evolution of life, as organisms living on different continents may become isolated from each other, creating unique ecosystems. When supercontinents begin to break apart, it leads to the formation of oceans and seas, which in turn facilitate the mixing of species and genetic exchange between different ecosystems. For example, the breakup of Pangaea, which occurred around 180 million years ago, resulted in the separation of dinosaurs into various groups, which then evolved into different species, adapting to new conditions. This process of isolation and connection of ecosystems creates a dynamic landscape of biological diversity that can be observed to this day. It is important to remember that tectonic processes continue, and in the future, we can expect new unification of land masses which will bring about new changes in climate and ecosystems. For example, in several 100 million years, when all continents reconnect, this could alter ocean currents, which in turn would affect the distribution of heat and moisture on the planet. Supercontinents, therefore, not only shape the physical structure of Earth, but also influence the development of life and ecosystems, creating conditions for constant change and adaptation of species. Over the past 100 million years, we have observed at least 3 major supercontinents, and each of them has had a significant impact on the biosphere of the planet, altering the evolutionary paths of numerous organisms. Supercontinent Pangaea existed approximately from 300 million to 200 million years ago, during the period known as the Mesozoic era. At this time, all the major landmasses were united into a single enormous continent, which had the shape resembling an elongated letter S, with a central part rich in diverse geographical features. Pangaea was surrounded by vast oceans, among which the Panthalassa Ocean stood out, occupying a significant portion of the planet. The climate on Pangaea was characterized by substantial fluctuations, with a vast arid zone in the center of the continent where rainfall was extremely rare. This created conditions for the formation of extensive deserts, such as the Gobi Desert, which also existed in this world at that time. On the coasts of Pangaea, where the continent met the ocean, the climate was significantly more humid. Monsoons brought seasonal rains, creating diverse ecosystems. However, on the majority of the landmass, a moderate climate was practically absent, which limited the diversity of flora and fauna. Such climatic conditions fostered the development of unique life forms capable of surviving in extreme conditions. For example, during this time, the first dinosaurs appeared, which adapted to various climatic zones, including both dry and wet territories. In the conditions of Pangaea, life developed within strict frameworks where species, such as ancestral reptiles, learned to migrate between different climatic regions to survive. Geological processes also exerted a significant influence on the climate, as tectonic movements created mountain ranges that could block moist air masses, forming arid regions. The vegetation on Pangaea included coniferous forests, as well as flora adapted to harsh conditions, where southern and tropical species dominated. Ferns and ginkgos were common plants in these forests. As a result of such a diversity of climatic conditions, Pangaea became a place where significant evolutionary changes occurred. The secrets of this unique continent continue to be studied by scientists who try to understand how its existence shaped modern life and climatic conditions on Earth. The existence of Pangaea was a significant milestone in the history of our planet, as evidenced by geological findings such as fossils discovered in areas now separated by oceans. The process of Pangaea's breakup began around 200 million years ago and continued over the course of tens of millions of years, resulting in the formation of today's continents and oceans. Initially, a vast continent began to slowly tear apart due to tectonic processes caused by the movement of lithospheric plates. These plates, which make up the upper part of the Earth, moved as a result of convective flows in the mantle, leading to the formation of cracks and faults in the Earth's crust. One of the first stages of the breakup involved the formation of narrow seas, such as the Tethys, which separated the northern and southern continents. Around 150 million years ago, during the late Jurassic period, significant changes began as the northern part of Pangaea, known as Laurasia, and the southern part, Gondwana, started to drift apart. This movement was as slow as it was inevitable, at a pace of several centimeters per year, which was more than sufficient to separate the continents over tens of millions of years. As a result of this process, a new ocean, the Atlantic, was formed, which initially was narrow but gradually widened with each million years. Around 100 million years ago, during the Cretaceous period, the Atlantic Ocean had already reached significant sizes, and its expansion created new marine routes and altered the migration paths of organisms. At this stage, the land continued to drift apart, and new seas formed between the continents, gradually becoming wider. Meanwhile, the continents began to take on more familiar shapes, which we see today. This was a time of monumental changes, as the Earth was reshaping itself and the climate and ecosystems were changing in response to the new geographical conditions. The breakup of Pangaea not only altered the world map, but also influenced the evolution of living organisms. New ecosystems emerged in isolated regions, and species adapted to the new conditions. By the end of the Cretaceous period, which concluded around 65 million years ago, the world looked completely different from the era of Pangaea. This process laid the foundation for further life development on Earth, and its consequences are still felt today, as each movement of the continents affects the climate and geography of the planet. There are geological evidence of this monumental process. For example, fossilized marine organisms found in mountains that were once at the bottom of the ocean confirm that the continents did indeed change their positions. In some places, such as the eastern coast of North America, one can see traces of this process in the form of faults and geological layers that testify to how the ocean slowly widened, separating what was once a single continent. The process of forming the Atlantic Ocean began more than 100 million years ago when Pangaea, the supercontinent, began to fracture into separate parts. As a result of this breakup, a narrow strait formed between modern-day Africa and America. Over millions of years, this strait gradually widened, eventually becoming the ocean we know today, which covers approximately 26 million square kilometers. The widening of the Atlantic Ocean was driven by the activity of mid-ocean ridges, such as the Mid-Atlantic Ridge, where tectonic plates spread apart and magma rises to the surface, forming new crust. This movement of plates created various ocean currents, such as the warm Gulf Stream, which begins its journey in the Gulf of Mexico and flows northward, influencing the climate of North America and Western Europe, making it milder. As the ocean expanded, so did the ocean currents, which were shaped by differences in water temperature and salinity. These changes over time affected the climate of the surrounding continents. Warm currents like the Gulf Stream contributed to a warmer winter in Europe, while cold currents such as the Labrador Current cooled the northeastern coast of North America. As the ocean expanded, its depth increased, creating new ecosystems and influencing the evolution of marine organisms. New marine routes emerged in the oceans, opening up possibilities for the migration and evolution of marine life. For example, the formation of new reefs and marine ecosystems, such as coral reefs, increased biodiversity, as new habitats attracted various forms of life. In tropical waters, warm currents facilitated the development of unique ecosystems that became home to various fish, mollusks, and corals. By the time the ocean reached its current size around 100 million years ago, it became a significant factor in shaping the climatic conditions and ecosystems we observe today. The study of these changes continues, and scientists like Dr. Mary Meggs from the Institute of Oceanography in Scranton are working on analyzing marine sediments to understand how these processes have influenced biological diversity and climatic conditions in the past. Current research indicates that rapid changes in ocean currents can lead to significant climatic consequences, including changes in temperature and sea level. Over the past few decades, for instance, a noticeable change in the temperature of the surface waters of the Atlantic Ocean has been observed, which could impact meteorological conditions in North America and Europe in the future. Volcanism is a process by which the internal energy of the Earth finds an outlet through fractures and cracks in the Earth's crust, expelling molten rock, known as magma, to the surface. Magma forms as a result of partial melting of rock in the mantle, located at depths ranging from 100 to 1,000 kilometers. Temperatures in this region reach between 1,000 and 2,000 degrees Celsius, creating conditions for the formation of molten materials. When pressure on the magma increases, it begins to rise to the surface, passing through cracks and fractures in the crust. This movement of magma is possible due to its lower density compared to the surrounding solid rocks. The process of volcanism also involves the release of gases such as water vapor, carbon dioxide, and sulfur dioxide, which are dissolved in the magma. These gases play a crucial role in the formation of volcanic eruptions, as their rapid expansion as the magma rises to the surface creates pressure that can break through the crust and cause an eruption. There are two main forms of volcanic activity: effusive, in which magma flows slowly onto the surface, forming lava fields, and explosive, when the pressure of the gases is so great that it results in powerful explosions, ejecting ash and debris into the atmosphere. Volcanism creates an atmosphere of constant tension between the internal forces of the Earth and the crust that holds them back, leading to the formation of the planet's relief, including mountain ranges and volcanic islands. For example, such mountain formations as the Andes in South America were formed as a result of long-term volcanic activity associated with the movement of tectonic plates, where one plate subducts under another, causing melting and the formation of magma. Plate tectonics, in turn, is a result of convective flows in the mantle, where hot rocks rise, cool, and sink again, creating cycles that have shaped the surface of our planet over millions of years. Volcanism also affects the climate by releasing large volumes of sulfur dioxide into the atmosphere, which can lead to the formation of aerosols that reflect solar radiation and temporarily cool the climate. One striking example of this is the eruption of the Pinatubo volcano in the Philippines in 1991, which resulted in a global temperature drop of 1 degree Celsius to 2 degrees for several years. Volcanism, therefore, is not just a destructive force, but an important process that shapes our planet, its climate, and its ecosystems. Since the internal forces of the Earth continue to act, it can be expected that volcanic activity will remain a part of the Earth's geological cycle for millions of years. Trap volcanicism refers to massive outpourings of basalt lava that occurred over millions of years and transformed the appearance of entire regions. An example of such eruptions are the traps of the Siberian platform, which formed at the end of the Cretaceous period, approximately 100 million years ago. These lava outflows occurred due to tectonic activity when fractures in the crust allowed magma to rise to the surface. The lava emerging from these fractures had low viscosity, enabling it to flow over large distances and form layers up to several kilometers thick. As a result of multiple eruptions, layers of lava accumulated, creating majestic stepped plateaus stretching over thousands of square kilometers. For instance, the traps in the area of modern Murmansk formed a powerful lava shield covering around 100,000 square kilometers. As the lava cooled, It formed characteristic geological formations such as columns and layers, which serve as the basis for future ecosystems. The stepped plateaus created by trap volcanism are characterized by flat surfaces and sharp cliffs that can reach heights of several hundred meters. These topographical changes influence climate and hydrological conditions, creating unique ecosystems where life adapts to specific conditions. Volcanic eruptions associated with trap volcanism occurred not only in Siberia, but also in other parts of the world. For example, in India, there are famous Deccan traps that formed around 65 million years ago, also as a result of massive eruptions. These traps cover an area of around 500,000 square kilometers and consist of numerous layers of basalt formed by multiple lava outflows. It is interesting to note that these eruptions could have played a significant role in the mass extinction of dinosaurs, causing global climate changes through the release of carbon dioxide and sulfur into the atmosphere. As lava flows, it disrupts existing ecosystems, and over time, it creates new biomes where unique plant and animal species evolve. The process of trap formation includes not only eruptions, but also subsequent erosion. Water, wind, and ice gradually erode lava layers, exposing older geological formations. This process allows scientists to study the history of Earth and the evolution of ecosystems. For example, in some areas of traps, scientists find fossils that help determine which animal and plant species existed at that time. Trap volcanism demonstrates how volcanic activity can not only destroy, but also create new landscapes that become homes for numerous living beings. Comparing traps with other types of volcanoes highlights the uniqueness of their eruptions. Unlike stratovolcanoes, which erupt viscous lavas forming cone-shaped structures, traps create extensive flat areas that can cover entire continents. This makes trap volcanism an important subject of study for geologists and ecologists who seek to understand how large-scale natural processes affect the biosphere. Research shows that trap volcanism can also influence climate. For example, powerful eruptions can release enormous amounts of ash and gases into the atmosphere, causing temporary temperature changes on Earth's surface. This is confirmed by data on climate fluctuations observed after major eruptions in Earth's history. Volcanic activity and the associated ecological changes remain relevant topics for scientific research, helping us better understand how such processes shape our planet. The number of known traps on Earth continues to increase with new geological discoveries, confirming that volcanism is one of the key forces shaping our planet's appearance. Trap volcanism remains an important part of Earth's history, leaving a significant mark in geology and ecology. Scientific research continues to reveal its influence on climate changes, ecosystems, and the evolution of life on Earth. Siberian traps, formed around 250 million years ago, are among the largest volcanic formations on the planet. These massive rocks, created by a series of volcanic eruptions, span an area of over 1 million square kilometers, stretching from the Urals to the Pacific Ocean. The traps were formed at the end of the Permian period and the beginning of the Triassic, when significant tectonic movements and climate changes occurred on Earth. Volcanic activity led to the release of enormous amounts of carbon dioxide and sulfur dioxide into the atmosphere, which in turn caused significant climate changes. For millions of years, the sky over Siberia was shrouded in a thick layer of volcanic ash, which blocked sunlight and created conditions similar to a volcanic winter. The air temperature dropped significantly, having a catastrophic impact on the flora and fauna of the time. Studies show that such conditions could have contributed to mass extinctions, including the Permian extinction, when around 90% of all species on Earth disappeared. This phenomenon is also linked to changes in the oceans, where the oxygen level dropped sharply, causing mass mortality of marine organisms. The volcanism of the Siberian traps acted as a catalyst for global climate changes, leading to the formation of acidic rains and other ecological disasters. Geologists believe that such events could be connected to changes in the composition of the atmosphere, which ultimately had long-term consequences for the biosphere. The Siberian traps are not only a geological phenomenon, but also a crucial element in understanding the interaction between volcanic activity and climate change. The volcanic rocks formed as a result of these processes are still studied by scientists to better understand their impact on the evolution of life on Earth. In particular, findings in the region indicate that new ecosystems emerged as a result of these eruptions, adapting to the changed conditions. Thus, volcanic activity led to the formation of vast lava fields and other geomorphological features that continue to influence the landscape of Siberia. In summary, the scale of these volcanic eruptions changed not only the climate, but also the fate of living beings, leaving traces in the geological history of our planet. The Siberian traps have become an important object of study for both geologists and climatologists who are trying to understand how such phenomena could recur in the future. Siberian traps formed around 250 million years ago served as a catalyst for one of the most extensive mass extinctions in Earth's history, known as the Permian extinction. This event, which occurred at the end of the Permian period, wiped out more than 90% of all species that inhabited the planet. The primary cause of this mass extinction was volcanic gases released during eruptions, which altered the chemical composition of the atmosphere and the oceans. Initially, a vast amount of carbon dioxide was released into the air, causing a greenhouse effect. The temperature on the planet rose and the climate became increasingly extreme. Studies by scientists have shown that the level of carbon dioxide in the atmosphere reached 3,000 parts per million, which is 3 times higher than the current level. This slow poisoning of the planet by carbon dioxide led to significant ocean acidification, which had a negative impact on marine life, particularly on organisms with calcium shells, such as mollusks and corals. Scientists like Dr. Jonathan Lambert conducted analyses of sedimentary rocks in the region of the Siberian traps and determined that ocean acidification occurred due to a sudden increase in the concentration of carbon dioxide and other acidic compounds. As a result of these changes, by the end of the Permian period, a vast number of marine organisms had disappeared, triggering a chain reaction in ecosystems. On land, there was also a significant reduction in biodiversity. Forests composed of tree ferns and conifers began to die out, leading to a decline in the number of terrestrial animals. Paleontological findings indicate that the changes in climate and ecological catastrophes caused by volcanic activity occurred over several thousand years. Volcanic eruptions, as research has shown, caused not only immediate destruction but also long-term changes that affected all levels of ecosystems, from microorganisms to large animals. These processes demonstrated how powerful geological forces can influence the climate and life on the planet as a whole. Mass extinctions are phenomena where a large number of species of living organisms disappear simultaneously, leading to significant changes in ecosystems and influencing the evolution of life on Earth. Throughout history, several such events have been recorded, each carrying lessons about the fragility of life. For example, at the end of the Permian period, around 250 million years ago, the largest mass extinction occurred, resulting in the disappearance of more than 96% of all marine species and more than 75% of terrestrial species. Research shows that this extinction was caused by a combination of factors, including tectonic movements, volcanic activity, and climate change. Such catastrophes create conditions where only the most adapted species survive, while many others fail to adapt to changing conditions. An important aspect is that mass extinctions not only destroy species, but also create new niches for the survival and evolution of other organisms. For instance, after the Permian extinction, dinosaurs began to develop and dominate ecosystems over millions of years. In later periods, such as the end of the Cretaceous period, around 66 million years ago, another mass extinction occurred, which led to the disappearance of dinosaurs and paved the way for mammals to become dominant in new ecosystems. These events demonstrate how life on Earth is influenced by various factors, from asteroid impacts to climate changes. Mass extinctions make us reflect on how quickly the face of the planet can change and how vulnerable life is in the face of radical environmental changes. It is important to note that even small changes in ecosystems can have catastrophic effects on many species, highlighting the need for a deep understanding of the interconnections in nature. For example, in the 20th century, scientists recorded a significant decline in the populations of many species due to anthropogenic factors such as pollution, climate change, and the destruction of natural habitats. Research shows that the current rates of species extinction are 100 times higher than natural rates. This raises serious questions about the future of the biosphere and what is happening to nature in the face of human activities. Each species that disappears carries unique genetic material and a role in the ecosystem, and with its disappearance, a part of the biological diversity that has been formed over millions of years is lost. Scientific research continues to reveal the connection between species extinction and the resilience of ecosystems, emphasizing that each species contributes to the overall well-being of the planet. As a result, mass extinctions remain a significant topic of study as they help us understand how living beings adapt to changes and how we can influence the future of our planet. It is important to remember that the fragility of life on Earth is not a new phenomenon, but a constant reality with which humanity must learn to interact. According to the World Wildlife Fund, by the 21st century, more than 1 million species are at risk of extinction, making the problem of mass extinction more relevant than ever. The Permian extinction, which occurred approximately 250 million years ago, was the most extensive known mass extinction in Earth's history. During this event, known as the Great Dying, up to 96% of all marine species and 70% of terrestrial species disappeared. This event was the result of a combination of factors, including rapid climate change, volcanic activity, and oxygen depletion in the oceans. For millions of years, life in the seas thrived. Trilobites, brachiopods, and microscopic organisms filled the waters. However, by the end of the Permian period, massive volcanic eruptions in Siberia, known as the Siberian Traps, released large amounts of carbon dioxide and sulfur, leading to global warming and oxygen depletion in the oceans. This caused a mass die-off of marine organisms. Corals that previously formed large reefs began to disappear, and ecosystems once teeming with life became desolate. Even entire groups of organisms, such as certain marine reptiles, could not adapt to the rapidly changing conditions.
On land, the extinction also took a heavy toll. Forests of conifers, which were home to many species, began to disappear, and herbaceous ecosystems struggled to cope with the encroaching desolation.
Paleontological data show that during this time, more than 80% of all plant and animal species on land went extinct. Many terrestrial predators and their prey, such as early reptiles, also faced food shortages, contributing to their extinction. As a result, ecosystems that were once diverse and full of life became desolate. Scientific research indicates that the recovery of ecosystems took millions of years, and the appearance of new species did not happen instantaneously. During the Triassic period that followed the Permian, life on the planet slowly rebuilt its positions, but in a different form. The recovery was a long and complex process, during which new species, such as dinosaurs, began to occupy the niches left vacant by the extinct inhabitants. This extinction was not only a catastrophe for many species, but also a crucial stage in the evolution of life on Earth, triggering processes that ultimately led to new biological diversity. The Permian extinction remains an active area of research, and scientists continue to study its causes and consequences to better understand how such catastrophes can impact the modern world. In the aftermath of this extinction, significant changes in the composition of flora and fauna occurred over millions of years, which continue to influence the biosphere and ecosystems of Earth. After the Permian extinction, Earth faced massive ecological changes. As a result of this event, approximately 90% of all animal and plant species went extinct, leaving behind a void that needed to be filled. On the planet, there emerged empty ecosystems where complex food chains were replaced by simplified structures. For instance, in marine ecosystems where trilobites and numerous other invertebrates previously dominated, now remnants of the few surviving groups, including some fish and mollusks like ammonites, prevailed. These changes created a new reality in which the surviving species began to occupy new ecological niches that were previously insufficiently filled. Evolution took its revenge. Approximately 50 million years after the extinction at the beginning of the Triassic period, evolution led to the emergence of new forms of life, such as dinosaurs and mammals. These groups began to fill the vacant ecosystems, which can be compared to a computer system reboot. The old versions were removed, and new, more adapted ones took their place. Paleontologists like Edward Dollo and his colleagues discovered that during this period, new ecological interactions began to develop, allowing mammals to gradually gain strength and diversity, while other groups, such as reptiles, gained dominant positions. The emergence of new species occurred rapidly as available resources and empty niches fostered their proliferation. As a result, in the Triassic, organisms such as the ancestors of modern crocodiles and the first mammals began to adapt to various habitats, from water bodies to forests. These changes influenced evolution over millions of years. One of the most striking examples is the appearance of the first dinosaurs, such as Eoraptor, which lived around 200 million years ago and became one of the first representatives of a group that dominated the Mesozoic era. As a result of this evolutionary reboot, ecosystems began to fill with new forms of life, and as shown by the paleontological record, significant changes occurred in the biosphere during the Triassic period. At this time, the diversity of flora also increased, with the appearance of such plants as conifers, which became dominant in terrestrial ecosystems, replacing the previously existing species. These changes in ecosystems laid the foundation for future biological interactions that later formed the familiar world to us. One of the most noticeable results of this process was that the survival and dominance of certain groups of species to a large extent determined the further evolution and adaptation on Earth. For example, by the end of the Triassic period, around 200 million years ago, the planet already had diverse groups of dinosaurs ready to occupy their places in food chains, forming ecosystems that would persist until the end of the Mesozoic era. Impact events refer to catastrophic collisions of Earth with large celestial bodies, such as asteroids and comets, which can instantaneously alter the conditions on the planet. These events can lead to widespread destruction, causing global catastrophes that affect the climate, ecosystems, and even biological diversity. For example, a collision with an object just a few kilometers in size can release energy equivalent to millions of atomic bombs, triggering tsunamis, forest fires, and dust clouds that block out sunlight. This creates conditions unsuitable for life and leads to mass extinctions of species. Throughout Earth's history, numerous impact events have occurred, each leaving its mark in the geological record. Scientists like Dr. William Scherer study fossils and sedimentary rock layers to understand the consequences of these collisions. For instance, approximately 60 million years ago, one of the most famous impact events occurred, leading to the extinction of dinosaurs when an asteroid about 10 kilometers in diameter struck Earth's surface. This collision released a massive amount of dust and debris into the atmosphere, causing sudden cooling and climate change. Short-term temperature and light changes altered the conditions of life on the planet, and many species could not adapt to the new realities. As a result, more than 75% of all species on Earth went extinct, making it one of the largest mass extinctions in history. Impact events highlight the fragility of planetary equilibrium in the face of powerful cosmic forces. Each such impact carries a threat capable of erasing millions of years of evolution. Research shows that even small asteroids passing close to Earth can pose a danger if they change their orbit due to gravitational interactions with other celestial bodies. The uncertainty in predicting such events, as well as the possibility of their sudden appearance, makes our planet vulnerable to the power of the universe. Scientists working in the field of planetary security continue to develop methods of protection, including tracking objects approaching Earth and studying ways to deflect their trajectories. This underscores that humanity must be prepared for potential threats from space and recognize that even the slightest change in orbit can lead to catastrophic consequences. Every day in space, collisions may be occurring that we are not even aware of, and their effects could be fatal for life on Earth. When a celestial body such as an asteroid or meteor enters Earth's atmosphere, it encounters immense air resistance, which causes it to heat up and burn up at altitudes ranging from 100 to 150 kilometers. During this process, a colossal amount of energy is released, equivalent to the explosion of several tons of TNT. For instance, the meteor that fell in Chelyabinsk in 2013 had a mass of about 7 tons and released energy equivalent to the explosion of around 50 kilotons of TNT upon entering the atmosphere. Upon impact with Earth's surface, the meteor creates a powerful shock wave that radiates radially from the impact point. This shock wave can cause destruction up to several tens of kilometers from the impact site. The shock wave also leads to the formation of a crater, which can reach a diameter of up to 10 kilometers, as seen in the case of the Chicxulub impact in Mexico, which is believed to have caused the mass extinction of dinosaurs around 65.5 million years ago. In this process, a central uplift forms, appearing as a cone-shaped structure in the center of the crater, where molten material is ejected into the atmosphere, creating clouds of gases and particles. This process is accompanied by the ejection of molten rock and debris, which can fall back to Earth within a radius of hundreds of kilometers, creating secondary craters. The propagation of seismic waves across the planet is also a result of the impact, and such waves can be registered by seismographs up to 1,000 kilometers from the epicenter. For example, the impact of a meteor in the Tunguska region of Russia in 1908 resulted in seismic waves that were recorded even in Europe. This underscores the devastating potential of the consequences of the collision of a celestial body with our planet and the extent to which its effects can spread. The Chicxulub crater is a colossal geological formation located on the Yucatan Peninsula in Mexico, which was created as a result of a meteorite impact approximately 65 million years ago. With a diameter of around 130 kilometers, it is one of the largest known craters on Earth. Scientists are convinced that this impact was the cause of the mass extinction of dinosaurs and many other species at the end of the Cretaceous period. The crater has a distinctive ring-like structure, and its age was determined using radiometric dating of rock samples found both inside and around the crater. This geological feature is surrounded by layers of sedimentary rocks that preserve evidence of catastrophic changes in the ecosystems of that time. The impact generated massive clouds of dust and smoke in the atmosphere, leading to global warming, followed by a rapid cooling event known as the nuclear winter. These changes resulted in the extinction of not only dinosaurs, but also more than 70% of all species on the planet. Within the crater, one can find fragments of ancient rock formations that indicate the impact caused powerful earthquakes and tsunamis capable of destroying coastal ecosystems. Research conducted in the 1990s under the leadership of scientists like David Kring resulted in a detailed map of the crater, helping to understand how the impact energy was distributed across the surface and its effects on the surrounding environment. The Chicxulub crater has become an important site for studying not only geology but also astrophysics, as it serves as a clear example of how cosmic events can influence the evolution of life on Earth. Small towns like San Felipe and Chicxulub are located around the crater and attract tourists interested in both geology and history. In this place where the cosmos intervened in the fate of Earth, one can observe how nature recovers from a catastrophe and understand how fragile life on our planet is. Some scientists continue to study the crater to uncover new aspects of its formation and the consequences of the impact, highlighting the significance of this geological feature for understanding the history of Earth. Today, the crater, covered in vegetation and surrounded by tropical forest, serves as a testament to how powerful natural cataclysms can reshape the face of the planet and life on it. An asteroid that collided with Earth and created the Chicxulub crater had a diameter of about 10 kilometers and was one of the largest celestial bodies recorded in history. It struck the planet's surface at a speed of around 60 kilometers per second, equivalent to approximately 220 kilometers per hour. The impact energy was estimated at around 10 billion megatons of TNT, which is roughly 1,000,000 times more powerful than the atomic bomb dropped on Hiroshima in 1945. This collision occurred approximately 65 million years ago and had catastrophic consequences for Earth's ecosystems. At the moment of impact, a flash of light was produced, its brightness being 1,000 times greater than the sun's light, causing instant vaporization of rocks and the ejection of massive amounts of stones and dust into the atmosphere. The temperature at the impact site reached several thousand degrees Celsius, leading to the melting and vaporization of a significant volume of Earth's crust. The crater formed in a matter of seconds, resulting in a depression with a diameter of about 140 kilometers and a depth of more than 20 kilometers. This crater became one of the largest on the planet and was buried under layers of deposits until it was discovered by scientists at the end of the 20th century. Materials ejected during the collision rose to the upper layers of the atmosphere and even into space, creating clouds of dust and debris that darkened the Earth's surface for many months, if not years. This led to a sharp cooling of the climate and changes in living conditions, which in turn contributed to the mass extinction of dinosaurs and other species. Research conducted by geologists and paleontologists has shown that this catastrophic event was a turning point in the evolution of life on Earth, opening a new chapter in the planet's biological history. The Chicxulub crater became not only a geological object, but also a symbol of how extraterrestrial forces can influence life on the planet. The Chicxulub impact caused a chain of catastrophic events that transformed the face of Earth and threatened the existence of life in a matter of hours. At the moment of collision, an asteroid with a diameter of around 10 kilometers released energy equivalent to billions of atomic bombs. This led to the creation of a firestorm that engulfed areas within tens of thousands of kilometers of the impact site. Temperatures in the epicenter reached thousands of degrees Celsius, igniting vegetation and forming gigantic fire tornadoes that tore through the atmosphere. Soon after, tsunamis with heights exceeding 100 meters struck the coasts of America and other continents. These colossal waves swept everything in their path, flooding coastal cities and destroying ecosystems that had existed for millions of years. Simultaneously, earthquakes caused by changes in geological structures shook the continents, creating fissures in the Earth's crust and contributing to the formation of new landscapes. Scientific research indicates that the strength of these earthquakes could reach 8 on the Richter scale, leading to the destruction of mountain ranges and the collapse of entire regions. Dust and debris clouds were thrown into the air, blocking sunlight and causing a sharp drop in global temperature. This phenomenon resulted in acid rain, which fell on the Earth, eroding soil and poisoning water bodies. Each of these factors alone constituted a catastrophe, but together they created an apocalyptic scenario where the familiar world crumbled in a matter of hours. Ecosystems that had evolved over millions of years were on the brink of complete annihilation. Paleontological research shows that it was during this period that approximately 75% of all species, including most dinosaurs, went extinct. The flora and fauna that existed at the time were unable to adapt to the sudden changes in climate and living conditions, leading to their rapid disappearance. Acid rain destroyed forests, while cold temperatures caused mass die-offs of warm-blooded animals. These events were pivotal in the history of life on Earth, paving the way for new species and ecosystems. As a result, the world as it was before the impact was forever lost to the past. The impact of Chicxulub caused not only immediate destruction but also long-term climate changes known as the impact winter. This term describes a sharp cooling of Earth due to a massive amount of dust and aerosols released into the atmosphere as a result of the collision. Scientists like Dr. William Allen from the University of Cambridge estimated that the dust and soot could have blocked sunlight for years, and in some regions, temperatures could have dropped to -10 degrees Celsius. As a result, photosynthesis, a vital process for plants and thus for all life on the planet, practically ceased. This meant that green plants, which formed the basis of food chains, began to die off, leading to the disappearance of many herbivorous animals that depended on them. Within the first few years after the impact, it is estimated that more than 90% of all plants on Earth disappeared. The decrease in oxygen levels and changes in carbon dioxide in the atmosphere led to more than half of all animal species being unable to adapt and becoming extinct. For example, giants like Triceratops and Tyrannosaurs were unable to survive this catastrophic event, leading to a significant decrease in biodiversity. Food scarcity led to fierce competition among the remaining species, marking the beginning of a new era known as the Late Cretaceous period. By the time the atmosphere began to clear over decades, ecosystems had already undergone irreversible changes. Research shows that during this time, entirely new species of animals and plants emerged, adapted to the changed environment. The impact winter may have lasted for several years, and the resulting massive climate stress led to significant changes in ecosystems. Fossil finds indicate that during this time, mammals and birds began to develop and adapt to the new conditions. Approximately 70 million years ago, about 500,000 years after the impact, the first primitive mammals appeared, which were able to occupy ecological niches left by the extinct dinosaurs. This process led to the formation of new ecosystems that eventually became the basis for modern biodiversity. Scientific research shows that it was during this period that new plant species began to form, becoming more resistant to climate changes. The restoration of ecosystems took millions of years, and only after a significant period of time did Earth return to a more stable climate, allowing new forms of life to evolve. 65 million years ago, one of the most catastrophic events in Earth's history occurred: the impact of the Chicxulub asteroid. This impact left a crater approximately 130 kilometers in diameter on the territory of present-day Mexico and caused global changes that led to the extinction of dinosaurs. These creatures, which had dominated the planet for over 150 million years, were unable to adapt to the abrupt changes in climate and ecosystems that followed the impact. As a result of the asteroid impact, a vast amount of dust and debris entered the atmosphere, preventing sunlight from reaching the Earth's surface. Temperatures dropped sharply, and a phenomenon known as the nuclear winter began. This was followed by massive changes in food chains. Plants that depended on sunlight began to die, directly affecting herbivorous dinosaurs such as Triceratops and Diplodocus. Herbivores were unable to find enough food, and their numbers rapidly declined. Carnivores like Tyrannosaurus rex and Velociraptor also faced threats as they lacked prey. It is known that approximately 97% of all dinosaur species became extinct as a result of this mass extinction. The remains of some species, such as ankylosaurs and stegosaurus, became rare finds in fossil layers, confirming their rapid disappearance. Natural selection, which had been acting for millions of years, did not have enough time to adapt dinosaurs to the new conditions, and they became victims of the sudden change in their habitat. Research shows that even magnificent creatures like brachiosaurs, with their enormous size and strength, were unable to survive in the new conditions. At this time, Earth began to rid itself of dinosaurs, paving the way for mammals and other forms of life that later became dominant on the planet. The science of paleontology actively studies this period, and fossil finds in various regions of the world, such as the United States and Canada, help to understand how this extinction unfolded. Scientists like David Pohl and Norman Newell reconstruct the ecosystems of that time based on data on the fauna and flora that existed before and after the Chicxulub impact. The magnificent dinosaurs, once seemingly invincible, became part of history, leaving behind only fossilized remains that contemporary scientists continue to study and interpret. The Mesozoic Paleogene extinction event marked the beginning of a new era in evolution, during which only a few groups of animals survived. Small mammals, such as rodents, were able to adapt to the new conditions by utilizing their ability to reproduce rapidly and colonize new territories. For instance, researchers from the University of Missouri in 2013 discovered that the small size of these animals allowed them to find shelter in cracks and under tree roots, providing protection from predators and harsh conditions. These mammals, such as the ancestors of modern mice and rats, not only survived but also began to proliferate, filling ecological niches left vacant by the disappearance of dinosaurs. Just as new plants begin to grow in the ashes after a forest fire, small mammals occupied the available space, leading to their radiation and the emergence of numerous new species. Birds also emerged as a successful group that survived the catastrophe. Their ability to fly provided them with a competitive advantage in the altered landscape. Studies conducted in 2015 by researchers from the University of Cambridge showed that some bird species, such as the ancestors of modern sparrows and pigeons, could use their flying skills to search for food over long distances. This allowed them to find food sources that were inaccessible to other animals, thereby enabling them to survive in resource-scarce conditions. Crocodiles and turtles also demonstrated remarkable resilience. These reptiles, adapted to semi-aquatic conditions, could survive long periods without food due to their slow metabolism. Research has shown that crocodiles can remain underwater for extended periods, allowing them to hide from predators and find food in more protected locations. Meanwhile, turtles colonized new territories using their digging abilities and the protection of their shells. As a result, they were able to occupy ecosystems that were previously inaccessible to other animals. The radiation of these groups of animals in the post-extinction period can be traced through fossil finds. For example, in 2006, fossilized remains of small mammals were discovered in South America, exhibiting clear signs of adaptation to the new environment. These species began to diversify, creating new ecological niches based on various food sources and habitats. Mammals, birds, crocodiles and turtles not only survived, but also began to fill the vacant spaces in the ecosystem. By the end of the Paleogene, around 60 million years ago, there were already groups of animals on Earth that became the ancestors of modern species. For instance, research conducted in 2019 showed that the ancestors of modern mammals began to diversify in various directions, leading to the emergence of groups such as primates and insectivores. Thus, the survival and further adaptation of these small but resilient creatures laid the foundation for the biodiversity we observe today. Supervolcanoes are magnificent, yet destructive, geological structures capable of ejecting enormous volumes of magma, ash and gas, reaching hundreds or even thousands of cubic kilometers. These volcanoes differ significantly from ordinary ones in both size and the power of their eruptions. While a typical volcano can eject several cubic kilometers of material in a single event, a supervolcano can produce an eruption that releases up to 1,000 cubic kilometers of magma into the atmosphere. Supervolcanoes form at the boundaries of tectonic plates, where magma accumulates beneath the Earth's crust, creating vast magma reservoirs. When the pressure in these reservoirs reaches a critical point, a catastrophic eruption occurs, which can alter the planet's climate for decades or even centuries. For instance, such eruptions can release significant amounts of sulfuric gas and ash, leading to a decrease in surface temperature. This phenomenon is known as a volcanic winter and can cause massive changes in ecosystems as well as affect agriculture, leading to famine and economic crises. Additionally, supervolcanoes can cause long-term changes in the atmosphere, increasing the number of aerosols and reducing the amount of sunlight reaching the surface. For example, in the 11th millennium before our era, one of the first known large supervolcano eruptions occurred, leading to a significant change in climate in Europe and Asia. Research shows that supervolcanoes can affect not only local ecosystems, but also global climate, impacting agriculture and human health over large areas. Scientists use various methods to study supervolcanoes, including the analysis of geological samples, modeling eruptions, and climate models to predict potential consequences. Methods for assessing supervolcano eruptions include studying layers of sediment left from previous eruptions, as well as using satellite technology to monitor changes in the Earth's crust. For example, using geodetic data, scientists can track surface deformations, which helps predict possible eruptions. Supervolcanoes not only interest geologists, but also pose a serious threat to humanity. The scientific community continues to study these giant structures to better understand their behavior and potential impact on our planet. It is important to note that supervolcanoes can remain dormant for thousands of years, but even minor changes in their activity can indicate an impending threat. Currently, several known supervolcanoes are located around the world, each representing a unique object of study, as their eruptions can have catastrophic consequences for life on Earth. Volcanologists continue to research their influence on climate, ecosystems, and even human civilization, emphasizing the importance of these giant geological formations in the context of global changes. Studying supervolcanoes is a critically important task for scientists, as understanding their dynamics and potential threats can help develop strategies to prevent and mitigate the consequences of their eruptions. Yellowstone caldera is one of the largest supervolcanoes on the planet, with dimensions reaching approximately 36 by 22 kilometers. The formation of this caldera resulted from several powerful eruptions, the most significant of which occurred around 600,000 years ago, when a massive magma ejection created a vast crater that we see today. Scientific research indicates that beneath the caldera lies a giant magma reservoir extending to a depth of about 10 kilometers. This magma is in a state of constant activity, making Yellowstone one of the most closely monitored volcanoes in the world. Monitoring systems installed throughout the park record thousands of earthquakes each year, some of which reach magnitudes up to 4 on the Richter scale. These subterranean tremors signal the movement of magma and gases beneath the surface. Volcanologists like Dr. Mary Hayes of the U.S. Geological Survey note that despite its apparent calm, Yellowstone is not dormant but merely awaiting its moment. The surface of this picturesque region is dotted with geysers and hot springs, such as the famous Old Faithful geyser, which erupts water up to 30 meters high every 80 minutes. These natural phenomena are just a small part of the vast volcanic mechanism hidden beneath lush forests and scenic lakes. For example, the temperature at the surface of some hot springs can reach as high as 132 degrees Celsius, indicating the incredible power beneath the Earth. Volcanic activity also influences the ecosystem of the region, creating unique conditions for flora and fauna. The Yellowstone caldera is one of the most studied geological formations, and its activity attracts the attention of scientists from around the world, who strive to understand how the magma and gas system interacts with the Earth's crust. The power hidden beneath this picturesque landscape serves as a reminder that nature can both create and destroy. In Yellowstone, where geysers and hot springs reveal only a fraction of the volcanic activity, scientists continue to study geological structures to predict future eruptions and assess their potential impact on the environment and population. Monitoring systems, such as GPS and satellite imagery, help track changes in the caldera and predict potential threats. Volcanic activity in this region not only threatens the ecosystem, but can also influence the climate in other parts of the world, as it did in the past when Yellowstone eruptions led to significant changes in weather conditions. 80,000 years ago, a powerful eruption released such large volumes of ash that it affected agriculture and climate in North America and even in Europe. There is a belief that events like the Yellowstone eruption can be catastrophic not only for the region, but for the entire world, as magma and ash emissions can cause global climate changes. Scientific research continues, and each year scientists find new evidence of the activity of this giant hidden beneath the beautiful landscape. In the year 38 AD, Yellowstone experienced its last major eruption, which was one of the most powerful volcanic events in Earth's history. Ash plumes reached heights of up to 30 kilometers, and the cloud of volcanic particles spread over thousands of kilometers, darkening the sky and altering the climate over vast areas.
Ash covered the ground to a depth of up to 2 meters within a radius of 100 kilometers from the crater, leading to a sharp decrease in sunlight.
As a result, temperatures in North America dropped by several degrees, causing significant changes in ecosystems. Vegetation, unable to adapt to the new conditions, began to wither and die under the weight of volcanic material. Agriculture was threatened as crops perished and many regions became uninhabitable. Studies show that such climate changes could have lasted for several years. According to climatologists, in some regions, temperatures remained below normal by 6 to 7 degrees for several seasons, leading to the inability of many animals and plants to survive. The ash and sulfur compounds released into the atmosphere formed clouds that trapped heat, exacerbating the global cooling effect. As a result, such conditions could have caused mass migrations of the population as people sought more favorable places to live. Climate change models based on the analysis of ice cores and other geological data show that the effects of the Yellowstone eruption were felt even on the eastern coast of the United States. Historians note that this event could have been one of the factors influencing the migration processes of indigenous peoples, as the changed climatic conditions forced them to leave their familiar territories. Scientific research continues to confirm that such volcanic catastrophes can affect global climate for decades, threatening not only ecosystems but also human lives. Consequently, such an eruption like the one in 38 AD could have led to mass famines and diseases, as evidenced by archaeological findings in areas where once flourishing civilizations existed. The volcanic activity of Yellowstone remains a topic of ongoing research, as scientists strive to understand how such catastrophes could impact the future of humanity. It is important to note that according to geologists' estimates, the next eruption could occur within the next few thousand years, and its consequences could be as devastating as those in 38 AD. The volcanic ash that fell to the ground consisted of glassy particles, minerals, and fragments capable of destroying ecosystems and altering the landscape. Supervolcano Toba on Sumatra is considered one of the largest and most powerful volcanoes on Earth. Its caldera, formed as a result of an eruption that occurred around 70,000 years ago, is approximately 130 kilometers long and 40 kilometers wide. This eruption was one of the most catastrophic in Earth's history, releasing a massive amount of volcanic ash and smoke into the atmosphere, which, according to scientists, caused global climate change and may have even led to a reduction in human population. At the bottom of this giant caldera, Lake Toba was formed, which is now the largest volcanic lake in the world. The lake covers an area of about 1,100 square kilometers, and its maximum depth is 400 meters. The water in Lake Toba has a bright blue color, and the surrounding mountains are covered in green forests, creating picturesque landscapes that attract tourists from all over the world. However, This serene view hides a potentially catastrophic power that could erupt at any moment. Toba regularly shows signs of activity, and recent small earthquakes and geysers in the area indicate that the volcano is not dormant. For example, in 2006, scientists registered an earthquake with a magnitude of 5.7, which served as a reminder of the need to monitor this supervolcano. Studies show that the eruption of Toba altered ecosystems over thousands of kilometers, and its effects were felt even in distant places like Europe and America. Comparisons with other supervolcanoes, such as Yellowstone, also highlight the importance of monitoring Toba, as its potential ash emissions could cause similar climate changes. Taking all these factors into account, Toba not only attracts with its natural beauty, but also represents a significant source of scientific interest and danger. There are data suggesting that the next level of activity could occur in the next few hundred or even thousand years, making the study of this volcano particularly relevant. Volcanologists like Professor David Patterson from the University of Missouri are working on creating models that will help predict possible scenarios of its activity. While many tourists enjoy the view of the lake and the surrounding landscapes, it is important to remember that beneath the surface lies a sleeping giant that could awaken at any moment. The eruption of the Toba volcano, which occurred around 74,000 years ago on the territory of modern-day Sumatra in Indonesia, is considered the most powerful volcanic event in human history. This eruption spewed a vast amount of ash and volcanic gases into the atmosphere, leading to catastrophic consequences for Earth's climate. Scientists estimate that during the eruption, around 1,000 cubic kilometers of material were released, which is 8 times more than the eruption of the Krakatoa volcano in 1883. As a result of this massive release, the sky remained covered with ash clouds for several years, leading to a sharp decrease in sunlight and, consequently, global cooling. The temperature on the planet dropped by several degrees, causing significant climate changes. Research indicates that the temperature could have dropped by 7 to 8 degrees Celsius over several years following the eruption. This cooling lasted possibly for up to 10 years, creating conditions in which agriculture became impossible. The temperature drop and climate change had catastrophic effects on early humanity, which, according to some estimates, numbered only a few thousand individuals at the time. Geneticists studying the DNA of modern humans suggest that the global catastrophe may have reduced the population to such an extent that representatives of Homo sapiens were on the verge of extinction. There are hypotheses that this event marked a sharp turn in human evolution, as the remaining groups began to migrate in search of more favorable living conditions. Some scientists link this event to the disappearance of large mammals, such as mammoths and woolly rhinos, which could not adapt to the new conditions. Volcanologists like Dr. David Satterley from the University of California in Los Angeles emphasize that the Toba eruption may have been one of the reasons why humanity experienced such a sharp decline and subsequent growth. This event left a deep mark on the history of our planet, changing both the climate and the biological diversity. There are also theories that the ecological changes caused by the eruption influenced the migration and development of cultural traditions among early humans. Scientific research conducted in the Toba region shows remnants of volcanic layers that confirm the date and scale of the eruption, as well as its consequences. As a result of these changes, significant shifts occurred in Earth's ecosystems, which shaped the planet's appearance over the course of millennia. Volcanic activity directly influences climate change through the release of gases and aerosols into the atmosphere. During eruptions, volcanoes emit large amounts of sulfur dioxide, carbon dioxide, and ash, which, upon entering the atmosphere, alter its composition. Sulfur dioxide converts into sulfate aerosols, which have the ability to reflect sunlight. This leads to a decrease in surface temperature as less solar radiation reaches the Earth's surface. For instance, over the past 30 years, scientists have found that a single large eruption can lower global temperatures by several degrees for several years, significantly impacting the climate. Aerosols formed from volcanic emissions can remain in the atmosphere for several months or even years, creating a persistent effect on the climate. Additionally, volcanic gases such as carbon dioxide can contribute to the greenhouse effect. Unlike sulfate aerosols, carbon dioxide traps heat in the atmosphere, leading to an increase in temperature. In this context, the interaction between volcanic activity and climate is a complex relationship. For example, while volcanic aerosols may temporarily cool the climate, elevated levels of carbon dioxide can contribute to long-term warming. This balance between cooling and warming effects can have a significant impact on meteorological conditions and ecosystems. As a result of temperature and precipitation changes, there can be substantial shifts in the distribution of vegetation and animal migrations, reflecting the deep connection between Earth's internal processes and its atmospheric system. Considering that these processes occur on geological timescales, it is evident how volcanic activity has shaped climatic conditions over millions of years. Data collected by meteorologists and geologists indicate that over the past 2 million years, there have been at least 13 major volcanic eruptions that have influenced global climate. These events have left their mark in geological layers as well as in climate archives such as ice cores and sedimentary rocks. Each of these elements underscores the importance of volcanic activity as one of the factors shaping Earth's climate system. The summer of 1816 became one of the most peculiar and tragic years in the history of Europe and North America, known as the Year Without a Summer. This anomalous event was caused by the catastrophic eruption of the Tambora volcano in Indonesia in 1815, which released an enormous amount of ash and sulfur into the atmosphere. As a result of this eruption, sunlight was partially blocked, leading to a sharp drop in temperature. The summer of 1816 became abnormally cold, with temperatures in some European regions falling 10 degrees Celsius below normal. In June and July, snow fell in places like New York and even in some parts of Europe, including Switzerland and Germany. This was completely unprecedented. Instead of the hot sun that people were accustomed to, they witnessed white flakes falling on blooming fields and gardens. Gardeners, expecting a bountiful harvest, were horrified when their crops froze before they could be harvested. As a result of this catastrophe, due to the lack of harvests, the prices of bread and other products skyrocketed, leading to famine in different regions. In Europe, especially in countries like Ireland and France, protests and riots broke out due to the shortage of food. People did not understand what was happening. Nature seemed to be confused, and many sought explanations in religious or mystical teachings. Writers and artists of the time, such as Mary Shelley and Lord Byron, were inspired by these events, creating works that reflected a sense of anxiety and uncertainty. Mary Shelley, who was in Switzerland, wrote her famous novel Frankenstein, which reflected the fear of nature getting out of control. Moreover, the anomalous weather not only affected agriculture, but also the health of people. Diseases such as typhus and dysentery broke out due to the lack of food and the deterioration of living conditions. In the United States, especially in New York, people gathered in groups discussing what to do next, and many naively believed that this was related to divine wrath. Farmers, desperate to save their crops, sought new ways of farming, which later led to changes in agronomy. This year left its mark on history as a period when nature demonstrated its power and unpredictability, and humanity faced its most acute challenges, awakening fear and the desire to find solutions. The uniqueness of the year without a summer lies not only in the climatic anomalies, but also in how these events affected society, changing its perception of nature and its own capabilities. Snow in July, the lack of harvest and famine became part of historical memory, a reminder of how fragile the balance between humans and nature is. The year 1816, known as the Year Without a Summer, had a profound impact on the culture and art of its time, giving rise to a number of significant works that transformed the literary and artistic landscape. One of the most striking examples is Mary Shelley's novel Frankenstein, published in 1818. Mary Shelley, along with her husband Percy Shelley and the poet Lord Byron, was inspired by the gloomy atmosphere created by unusual weather conditions during their stay in Switzerland in the summer of 1816. Unrelenting rain and a cold summer produced a depressing mood that was reflected in her work about the creation of an artificial human and its struggle with society. The novel explores themes of human nature, moral responsibility, and the consequences of scientific progress, making it relevant even today. During this period, artists such as John Constable and Caspar David Friedrich began creating dark landscapes filled with a sense of despair and melancholy. Friedrich's works often depicted solitary figures against desolate, misty landscapes, reflecting the inner turmoil of people in the face of natural disasters. His painting, The Wanderer Above the Sea of Fog, created in 1833, symbolizes the loneliness of a person confronted by the vast and unpredictable forces of nature. Literature of the time also mirrored apocalyptic sentiments. Works such as Lord Byron's Childe Harold's Pilgrimage and John Keats' Lamia are filled with images of fear and desolation, indicating how the catastrophe affected society's consciousness. These authors, like Shelley, sought meaning in chaos and tried to understand how nature could be both a source of inspiration and a threat. Ultimately, the cultural impact of The Year Without a Summer served as a catalyst for the creation of classic works that not only reflect the fears of their time, but continue to resonate with readers and viewers today. For instance, Frankenstein remains one of the most adaptable texts, serving as the basis for numerous films, theatrical productions, and studies exploring the boundaries between humanity and technology. The significance of these works lies not only in their artistic expression but also in their deep reflections on human essence and humanity's place in a world where nature can manifest both beautiful and destructive forces. Glacial periods are key moments in Earth's history when vast masses of ice covered significant portions of continents. These cycles of cold and warmth have occurred over millions of years, creating unique conditions for the formation of landscapes and ecosystems. For instance, during the maximum extent of glaciation, which could reach up to 30% of continental surfaces, ice sheets extended over thousands of kilometers. The slow but inexorable movement of ice has led to significant changes in Earth's topography. Glaciers carved deep valleys and formed fjords, such as the famous Norwegian Geiranger Fjord, which is approximately 15 kilometers long and was created by glacial activity. These ice masses also altered river systems, creating new bodies of water and changing river courses. For example, the Mississippi River has its origins in glacial processes. When glaciers retreated, they left behind richly sedimented plains that fostered the formation of fertile soils. The movement of ice was not only destructive, but also constructive, contributing to the formation of geological features such as moraines and gravel ridges, which mark the boundaries of glaciers. These formations are direct witnesses of glacial activity and can reach heights of up to 30 meters. Glacial cycles, spanning tens of thousands of years, are the result of complex climatic changes caused by both natural and anthropogenic factors. Variations in solar radiation, tectonic movements, and fluctuations in atmospheric carbon dioxide levels influence the planet's temperature and contribute to the onset and termination of glacial periods. For example, over the past 2.5 million years, at least 15 major glacial periods have occurred, each leaving its mark on Earth's surface. Glaciers, moving at a pace of just a few centimeters per year, can reshape entire continents over millions of years, altering their landscapes and ecosystems. For instance, the Laurentide ice sheet, which covered much of North America, extended from Canada to the northern states of the US, leaving behind characteristic features such as lakes and hills. The formation of the Great Lakes, including Lake Superior, is linked to the retreat of this ice sheet, which left behind vast basins that filled with water. glacial activity also played a significant role in the evolution of flora and fauna. Many species, such as the mammoth and the woolly rhinoceros, were forced to adapt or go extinct in the face of climate and habitat changes. Research shows that more than 30% of all mammalian species went extinct as a result of changes brought about by glacial periods. It is important to note that these changes did not occur instantaneously. They spanned thousands of years, and the adaptation of species to new conditions was a lengthy process that also contributed to the increase in biological diversity on the planet. Therefore, glacial periods represent not only important climatic events, but also catalysts for geological and biological changes on Earth. These processes continue today, albeit in a modified form, and their influence is felt in the modern climate and ecosystems. For example, contemporary research shows that the melting of glaciers in Greenland and Antarctica is accelerating, which could lead to a rise in sea level by several meters in the future. It is crucial to remember that glacial periods are not just historical events. They are ongoing processes that continue to shape our planet and influence life on it. The last glacial maximum occurred around 20,000 years ago, when vast masses of ice covered a significant portion of the northern hemisphere. The Laurentide ice sheet, stretching from Canada to Scandinavia, reached thicknesses of up to 3 kilometers in some areas. At this time, sea levels dropped by approximately 120 meters compared to their current state, uncovering new land and creating bridges between continents. For instance, the Bering Strait, which now separates Asia from North America, became a land bridge, facilitating the migration of animals and people. Climates changed significantly. Regions that are now home to warm forests were once characterized by harsh tundra and steppe conditions, inhabited by unique fauna such as mammoths, woolly rhinos, and saber-toothed tigers. These animals adapted to the cold climate with thick fur and massive bodies that helped retain heat. In such conditions, there were also small reindeer and giant birds like the South American rhea, which could survive due to the abundance of vegetation that regenerated during the warm periods between glacial epochs. Glaciers created numerous lakes and rivers, such as Lake Michigan and the St. Lawrence River, which formed as a result of ice melt. These bodies of water, in turn, became important ecosystems for diverse fauna and flora. Cold, hardy plants like mosses and lichens covered extensive areas, forming the basis for complex ecosystems where animals thrived. At this time, climatic conditions also favored the formation of permafrost, which preserved organic matter and contributed to the development of specific ecosystems. These changes in climate and landscape left an indelible mark on human history, as hunter-gatherers began to adapt to the new conditions, which later laid the foundation for the formation of the first societies. The period of the last maximum ended around 10,000 years ago when global warming began, leading to the melting of glaciers and the transformation of ecosystems, which resulted in the formation of new climatic zones in the northern hemisphere. The last ice age, which lasted from approximately 180,000 to 10,000 years ago, was home to megafauna, including giants like mammoths and woolly rhinos. Mammoths, reaching heights of up to 4 meters and weighing up to 6 tons, were covered in thick fur that helped them survive in the harsh conditions of the Arctic tundra. They moved in herds, and their powerful tusks, up to 4 meters long, were used for foraging under thick layers of snow and for defense against predators. Woolly rhinos, with their massive bodies and distinctive large horns, also inhabited these cold regions and fed on grasses and shrubs that grew in the tundra. Their size and strength allowed them to compete with other herbivores, such as bison and deer, for resources. At the same time, these ecosystems were home to cave bears, which could reach weights of up to 1 ton and lengths of up to 3 meters. These predators typically hunted small mammals, but could also attack young mammoths or rhinos using their strength and keen sense of smell. Saber-toothed cats, or smilodons, were even more formidable predators, with long canines reaching up to 25 centimeters. These cats adapted to hunting in open landscapes, using their powerful hind legs for swift attacks on large herbivores. Their acute physical form and ability to hunt in packs made them some of the most dangerous predators of their time. All these species were intricately interconnected, creating a unique ecosystem where giant herbivores maintained balance and predators controlled populations, preventing overpopulation. For example, during this time, giant sloths also inhabited these ecosystems, reaching lengths of up to 4 meters and weighing more than 1 ton. They fed on leaves and branches, adding diversity to this complex food chain. Moving to more southerly latitudes, megafauna adapted to various climatic conditions, resulting in the formation of unique ecosystems in different regions. For instance, in North America, in areas with less harsh climates, one could encounter mastodons, which were similar to mammoths but had shorter tusks and less massive bodies. They also played a crucial role in the ecosystem, aiding in seed dispersal and maintaining plant health. This harsh but dynamic world of megafauna was teeming with life and interactions, where each individual, from giant herbivores to predators, played its part in maintaining the ecosystem. To better understand how megafauna influenced its environment, it is worth noting that their extinction at the end of the last ice age was linked to climate change and human hunting, leading to the disappearance of these remarkable creatures. Scientists believe that over the past 10,000 years, more than 100 species of megafauna have gone extinct, altering ecosystems and opening new niches for other species. At the end of the Pleistocene, approximately 12,000 years ago, a significant retreat of glaciers began, liberating vast territories from the ice cover that had previously occupied much of North America and Eurasia. Glaciers, such as the Laurentide, which extended from modern Quebec to the central part of the United States, started to recede, opening up new lands for colonization by plants and animals. As a result of this process, new lakes formed, such as Lake Superior and Lake Michigan, and new river systems emerged, providing habitats for diverse aquatic ecosystems. The global sea level gradually rose, also contributing to changes in coastal ecosystems. Research indicates that during this time, the sea level rose by about 100 meters, altering the contours of continents and leading to the flooding of some low-lying coastal areas. With the retreat of the ice, ecosystems began to change. Coniferous and deciduous forests started to move northward, replacing tundra and taiga. According to paleobotanists, trees such as pines and maples began to appear in regions previously covered by ice, creating new habitats for animals. This process took several thousand years, and by 7,000 years ago, forests had reached the southern borders of Scandinavia and western Siberia. As forests expanded, biological diversity increased. New species of mammals, such as deer and bears, began to populate these ecosystems. Meanwhile, in the south, where the climate became warmer and wetter, broadleaf forests emerged, providing habitats for numerous bird and insect species. Scientific data show that as vegetation increased, the level of carbon in the atmosphere also changed, further altering the climate. The last ice age left not only physical changes in the landscape, but also profound traces in biological diversity, shaping the ecosystems we observe today. The replacement of tundra by forests also led to changes in soil composition, as the soils became more fertile and contributed to the development of agriculture in the future. Forests absorbed carbon, which in turn influenced the global climate, creating conditions for new forms of life. These changes in ecosystems became the basis for the formation of new biomes, such as the taiga, which occupies a significant part of northern Eurasia, and mixed forests, which became the dominant element of the ecosystems of the temperate zone. As vegetation increased, animals adapted to the new conditions, and some species, such as mammoths and woolly rhinos, began to disappear, giving way to more modern representatives of fauna that could adapt to the new environmental conditions. Parallel to this, the climate continued to change, leading to further development of ecosystems and adaptation of existing species. During the melting of glaciers, catastrophic floods occurred, which radically altered the landscape. As a result of the breakthrough of glacial lakes, such as Lake Missoula in North America, water rushed down with immense force, destroying everything in its path. This catastrophe happened approximately 14,000 years ago and led to the formation of megafloods that changed the relief of entire regions in a matter of days. The Missoula flood, considered one of the most powerful in history, released around 400 cubic miles of water, equivalent to billions of gallons. The water bursting from the lake was due to the melting of glaciers that formed natural dams, which eventually gave way under the pressure. This process resulted in the formation of a specific landscape known as scabland, where water carved new valleys and canyons, eroding rocks and creating impressive geological structures. As a result of these catastrophic events, the Columbia Canyon was formed, stretching over more than 400 kilometers, where deep chasms and sheer cliffs are a testament to the uncontrolled power of water. Such events did not occur only in North America. In Europe, particularly in Sweden and Norway, the breakthrough of glacial lakes also led to massive floods, shaping unique landscapes. In these regions, researchers discovered traces of ancient riverbeds that were carved by water flows reaching speeds of up to 100 kilometers per hour. These water flows could move massive boulders weighing tons, transforming peaceful plains into raging rivers. Scientists such as David C. Hughes of the University of California have found that such floods not only altered the physical appearance of the Earth, but also significantly affected ecosystems, leading to the extinction of some animal and plant species that could not adapt to the new conditions. The breakthrough of glacial lakes created new ecosystems but also destroyed familiar ones. As a result of these catastrophic events, new conditions emerged on Earth, giving rise to new flora and fauna adapted to the changed conditions. These massive changes occurred sometimes in just a few days, leaving behind only traces in the form of new geological formations and deep canyons. Water breaking away from glaciers left behind colossal traces, and it is these events that have shaped the world as we know it today. Scientific research shows that such floods occurred regularly over thousands of years, and their effects were felt even long after the events. For example, in Eastern Africa, around 30,000 years ago, similar floods changed the courses of rivers and formed lakes that still exist today. At the end of the Pleistocene, around 10,000 years ago, Earth faced global climate changes that acted as a catalyst for the extinction of megafauna. Mammoths, mastodons, giant sloths, and many other large mammals that formed unique ecosystems during the Ice Age began to disappear from the face of the planet. Climate changes led to warming, which altered the habitual habitats of these animals. For example, mammoths, which inhabited vast territories from North America to Eurasia, depended on cold steppes and tundras filled with grasses and shrubs. Their extinction was due not only to climate change, but also to the growing pressure from human populations. Archaeological findings show that people began actively hunting mammoths using stone tools such as spears and harpoons, which significantly reduced their numbers. In particular, in North America, large mammals, including mastodons, were subjected to intense harvesting, and by 4,000 years ago they had completely disappeared. Scientific research conducted by paleontologists shows that the combination of hunting and climate change led to the destruction of ecosystems where megafauna existed. For instance, giant sloths reaching lengths of over 3 meters were also unable to adapt to the new conditions and disappeared from the face of the Earth. The establishment of a warmer and drier climate, as well as the development of forests instead of open spaces, threatened the survival of these species. It is important to note that megafauna played a key role in maintaining ecosystems, including the dispersal of seeds and maintaining the diversity of flora. The extinction of species like the shaggy rhino was also linked to climate change and human activity. ultimately leading to the formation of new ecosystems. As a result, by the end of the Pleistocene, many species that once dominated ecosystems went extinct, leaving behind only fossil remains. These changes in ecosystems, which occurred over a relatively short period, clearly demonstrate how fragile nature is when faced with climate changes and human activity. Megalodon, one of the largest predators ever to have existed on Earth, also disappeared around the same time, underscoring the scale of the extinction during that period. Consequently, by 8,000 years ago, only small groups of large mammals, such as bison and bears, remained on Earth, which were able to adapt to the new conditions. Meteorite craters are not just simple depressions on the surface of the Earth. They are evidence of cosmic catastrophes that have occurred on our planet over millions of years. Each crater is a window into the geological history, allowing scientists to study the consequences of Earth's collisions with asteroids and comets. According to estimates, Earth is struck by cosmic bodies on average once every few thousand years, and each such impact can have catastrophic consequences for ecosystems. For example, it is believed that a meteorite with a diameter of about 10 kilometers, which struck Earth around 65 million years ago, was responsible for a mass extinction, wiping out more than 70% of all species on the planet. This impact created a crater with a diameter exceeding 100 kilometers, and its effects were felt not only in the immediate vicinity of the impact site, but also over vast distances, causing global climate change. It is important to note that the traces of these impacts are preserved in the geological record, including layers of sedimentary rocks that may contain unique minerals formed as a result of high temperatures and pressures. Geologists analyzing these layers can determine the time and strength of the impact, as well as its effects on the surrounding environment. For instance, some craters contain fossilized remains of animals and plants that lived at the time of the impact, providing insight into how life on Earth adapted to new conditions. Meteorite craters can also be filled with water, forming crater lakes that become ecosystems with unique flora and fauna. These craters serve not only as scientific objects, but also remind us of how vulnerable Earth is to cosmic forces. Each crater is not just a geological formation, it is a reminder that our planet is constantly subjected to external influences that can alter its appearance. Scientific research indicates that Earth may face new collisions in the future, making the study of meteorite craters an important step in understanding not only our history, but also our prospects for existence. Each impact, leaving its mark in the form of a crater, serves as a reminder that Earth is not a protected fortress, but a part of a dynamic and sometimes dangerous ecosystem interacting with the cosmos. As a result, the study of these craters helps scientists predict the possible consequences of future cosmic collisions. Meteorite craters around the world preserve not only physical evidence of catastrophes, but also information about how life on Earth has survived, adapted, and ultimately recovered from such events. The meteorite crater in Arizona, known as the Arizona Crater, is one of the most impressive and well-preserved craters on Earth. Its diameter is approximately 1 kilometer, and its depth exceeds 100 meters. This crater was created about 50,000 years ago when a meteorite the size of a car, weighing around 30 tons, struck the Earth's surface at a speed of about 20 kilometers per second. The energy released in this collision is equivalent to the explosion of an atomic bomb. Standing at the edge of the crater, a person feels small in comparison to this gigantic wound in the Earth's surface, which is a result of a catastrophic event. Visually, the crater is striking with its steep walls that drop into the bottom, where exposed layers of rock can be seen, representing a historical record of changes in the Earth's crust. The sun, reflecting off the crater walls, creates captivating plays of light and shadow, emphasizing its size and depth. Viewed from above, the crater appears as a massive eye looking up at the sky, its edges jagged and precipitous, evoking a sense of the immense power of nature and time. Mountains surround the crater, and its floor is covered with gravel, and small stones that remind one of the meteorite that left this mark in history. Scientists and tourists from around the world visit this site to study both the crater itself and the surrounding landscape, which has been altered by this impact. The crater has become not only an object of scientific study but also a symbol of the power of nature, demonstrating how quickly and suddenly catastrophic changes can occur on the planet. For example, in the 20th century, the crater became a site for aerospace research, particularly related to the study of meteorite impacts. On February 18, 2003, NASA conducted tests of a special probe that simulated meteorite impacts to study the consequences of such collisions on the planet's surface. As a result, the crater has become not only a geological object but also an important test site for experiments related to protecting Earth from future threats. The well-preserved structure of the crater allows us to see what the consequences of a meteorite impact look like and understand the role such events played in the history of our planet. Research shows that similar craters can be found on other planets and moons, opening new horizons for the study of cosmic processes and their influence on geology. The Popigai crater is located in a remote corner of Siberia, in an area known for its harsh nature and difficult accessibility. This crater, formed approximately 130 million years ago as a result of a meteorite impact, is one of the largest impact craters on Earth, with a diameter of 180 kilometers. Its location, hidden among the taiga and marshes, makes its study a real challenge for scientists. Research conducted by Russian geologists in 2001 showed that the crater has retained its original forms and structures, allowing scientists to study the consequences of cosmic catastrophes and their impact on geological processes. Unique impact diamonds were found inside the crater, formed under the influence of high temperatures and pressures caused by the impact. These diamonds differ in composition and structure from ordinary ones, forming under conditions that cannot be replicated on Earth's surface. During excavations in 2005, researchers found samples of impact diamonds containing minerals not found in ordinary conditions. These diamonds are usually in the form of microscopic crystals, often surrounded by other minerals, indicating their unusual origin. The uniqueness of the Popigai crater lies not only in its geological structure, but also in the layers that were deformed and destroyed by the impact, allowing scientists to study not only the consequences of the impact, but also the age of the surrounding rock formations. Research expeditions conducted since the early 2000s have shown that the crater contains a large number of rare minerals, such as corundum and spinel, formed as a result of thermal effects. Complex research by scientists from the Russian Geological Institute has confirmed that the Popigai crater can become an important object for studying not only impact geology, but also processes occurring on other planets, such as Mars and Venus, where traces of meteorite impacts have been found. Scientists believe that studying this crater can help understand how Earth might react to larger cosmic threats in the future. 80% of the crater's territory is covered by forests and small water bodies, making its study even more complex and interesting. Scientists working in this region face many difficulties, including harsh climatic conditions that can significantly complicate fieldwork. Nevertheless, the Popigai crater continues to be an object of interest for geologists and mineralogists striving to unravel its mysteries and understand how such events have shaped not only our planet, but the entire solar system. Discoveries made in this unique place can change our understanding of geological processes and cosmic catastrophes that have occurred over millions of years. In 2006, samples were found in the crater that were later described in scientific publications, confirming the existence of impact diamonds formed as a result of a meteorite impact. Today, the Popigai crater remains one of the most mysterious and studied territories on Earth, with its unique natural resources continuing to attract the attention of scientists from around the world. In 1908, at the dawn of the 20th century, a powerful explosion occurred in Siberia, known as the Tunguska event. This phenomenon took place on June 16, 1908, at 1420, when a celestial body, likely a meteorite or comet, entered Earth's atmosphere and exploded at an altitude of approximately 5 kilometers above the Taiga. The energy of the explosion was estimated to be around 15 megatons in TNT equivalent, which is several times more powerful than the atomic bomb dropped on Hiroshima. This resulted in catastrophic damage over an area of about 2,000 square kilometers. Trees were uprooted from the ground, and those that remained standing were charred and felled within a 30-kilometer radius of the epicenter. Remarkably, no crater was observed, as is typically the case with meteorite impacts, which has given rise to numerous theories and hypotheses. Researchers, such as the Soviet scientist Viktor Kulikov, who first began studying the site in the 1930s, faced difficulties due to the remoteness and inaccessible nature of the region. The taiga, densely populated with diverse flora and fauna, lacked convenient access routes and posed a challenge for scientists. Official expeditions began only decades later, when geographical conditions became more favorable for research. It was not until 1953 that a group of scientists led by academician Anatoly Koptyuk was able to conduct a more detailed investigation, collecting soil and wood samples that showed anomalous levels of radiation. This enigma has captivated scientists for over a century, giving rise to not only scientific but also fantastic theories about the extraterrestrial origin of the event. Many researchers believed it could have been a visit by extraterrestrials or a test of secret weaponry, but none of these theories have provided conclusive evidence. As a result, the Tunguska event remains one of the most intriguing mysteries of science, attracting interest not only from physicists and astrophysicists, but also from cultural anthropologists studying its impact on the folklore and mythology of local peoples. In recent years, with the advancement of technology, researchers have revisited this topic, using modern satellite technologies and ground-penetrating radar to attempt to unravel the nature of the event and understand its impact on the surrounding environment. In 2020, a new expedition was conducted, during which scientists discovered anomalous concentrations of carbon oxide and other substances in the soil, which may indicate unique chemical reactions that occurred as a result of the explosion. The Tunguska event continues to be an unsolved puzzle, attracting the attention of both scientists and enthusiasts of mysteries, and each new step in its study opens new horizons for research. February 2013 marked the day when Chelyabinsk encountered a cosmic threat that many had not even suspected. At 9:20 a.m., a deafening crack echoed over the city, reminiscent of a colossal explosion. This was a meteorite the size of a bus, entering Earth's atmosphere at a speed of around 18 kilometers per second. A bright flash of light, visible for hundreds of kilometers, illuminated the sky, followed by a shockwave from its piercing motion, shattering windows in over 7,000 buildings. The incident resulted in approximately 1,500 people injured, most of whom suffered minor injuries from flying glass. The meteorite, which weighed around 70 tons, destroyed buildings, blew out doors, and left a trail of devastation as if a hurricane had swept through the city. Special services and volunteers began searching for meteorite fragments that fell near Chelyabinsk and in Lake Chebarkul from the first moments. For several days after the event, volunteers, local residents and scientists scoured the area within a radius of several dozen kilometers for fragments. Many small fragments were found, with the most significant piece weighing around 1.5 kilograms and being recovered from the lake at the end of February. This piece became the subject of study for scientists who sought to determine its composition and origin. The research revealed that the meteorite belonged to the chondrite group, confirming its ancient cosmic status. Meanwhile, discussions about the need to improve early warning systems for such threats were underway in the city. These discussions involved not only scientists but also ordinary residents who realized how fragile their daily lives were in the face of cosmic catastrophes. The Chelyabinsk meteor became a vivid example of how extraterrestrial objects can intrude into our lives, changing them in an instant. The incident led many to ponder how unprepared humanity is for such events, and how crucial it is to have mechanisms for protection and response to such threats. The city's recovery from the impact took several weeks, and many residents witnessed how daily life can be abruptly disrupted by something from the sky. The Chelyabinsk meteor left not only physical traces in the form of fragments, but also became a symbol of the constant presence of cosmic dangers above us. Tsunamis are powerful ocean waves that can occur as a result of underwater earthquakes, landslides, or even asteroid impacts. The process of their formation begins with a sudden displacement of a large mass of water, which happens, for example, during earthquakes when tectonic plates shift. This releases a tremendous amount of energy, creating waves that can travel at speeds up to 80 kilometers per hour in open ocean. These waves are often imperceptible to ships, as their height can be only a few dozen centimeters, and the distance between crests can reach 100 kilometers. In open sea, a tsunami appears as a small ripple on the surface, creating a deceptive sense of calm, and many people do not even suspect the impending danger. However, as the waves approach the shore, where the ocean depth decreases, they begin to accumulate energy and increase in height. This process is called wave sharpening. When a tsunami reaches shallow water, its height can rise to 30 meters or more, transforming into a powerful and destructive wall that crashes onto the shore with devastating force. Such waves can sweep away everything in their path, destroying buildings, uprooting trees, and causing mass evacuations. Statistics show that the speed at which a wave moves in shallow water can reach 40 kilometers per hour, and people often do not have enough time to prepare for such an unexpected and massive disaster. The impact force of a tsunami is comparable to a nuclear explosion. Even small waves can cause catastrophic consequences if they strike populated areas. The previously described mechanisms of tsunami formation explain why it is important to closely monitor seismic activity in coastal regions. These knowledge can save lives, as a warning about a possible tsunami can give people a few minutes to evacuate. There are special early warning systems that track underwater earthquakes and can predict the appearance of a tsunami in just a few minutes. However, in practice, even with the most advanced technologies, it is impossible to stop the power of these waves. As a result, tsunamis remain one of the most dangerous natural phenomena, capable of causing significant destruction and loss. It is important to remember that tsunamis not only threaten human lives but also have long-term consequences for ecosystems, altering the landscape and disrupting the natural flow of life. The tsunami in the Indian Ocean in 2004 was one of the most devastating natural disasters in human history. The cause of this tsunami was a powerful earthquake of magnitude 9.0 that occurred on December 26, 2004, off the coast of Sumatra, Indonesia. This earthquake happened at the boundary of two tectonic plates, the Indo-Australian and Eurasian, and caused a sudden uplift of the seafloor by several meters. The waves generated by this uplift began their rapid movement in various directions, crossing the Indian Ocean at speeds up to 300 kilometers per hour, comparable to the speed of a jet aircraft. As they approached the coasts of countries surrounding the ocean, the waves gained strength and height, changing depending on the underwater terrain and the configuration of the shoreline. On open water, the wave height was only a few tens of centimeters, but as they approached the shore, especially in narrow bays and inlets, they grew significantly, reaching heights of up to 30 meters. For example, on the coasts of Indonesia and Sri Lanka, the waves struck with catastrophic force, destroying everything in their path. In Indonesia, the province of Aceh was particularly hard hit, with entire villages destroyed and more than 200,000 people dead. In Sri Lanka, where the wave hit the eastern coast, around 36,000 people perished and millions were left homeless. In Thailand, on the resort island of Phuket, The waves also caused significant damage, destroying hotels and sweeping tourists into the sea. As a result of this catastrophe, more than 12,000 victims were registered in the province of Aceh alone, and the total damage was estimated in the billions of dollars. The tsunami also affected many islands, including the Maldives, where waves destroyed infrastructure and led to mass evacuations. Rescue operations began almost immediately after the disaster, but many people remained without help for several days. The recovery of affected regions took years, and some places still have not fully recovered from the aftermath. An interesting fact is that this tsunami served as a catalyst for global changes in the tsunami warning system, leading to the creation of new technologies and monitoring systems. The tsunami of 2004 had a catastrophic impact on the coastal ecosystems. Mangrove forests, which served as natural barriers and homes for numerous animal species, were almost completely destroyed. According to ecologists, the loss of mangrove forests exceeded 60% in countries like Indonesia and Thailand. These forests not only protected the coast from erosion, but also provided habitats for fish, crustaceans, and birds. Based on data collected in 2006, the restoration of mangrove ecosystems may take several decades, as mangrove seeds germinate slowly and require specific conditions for growth. Coral reefs, which were also affected by the wave, faced additional challenges. Research conducted in 2008 showed that around 70% of coral reefs in the Indian Ocean were damaged. These reefs not only support marine biodiversity but also play a crucial role in protecting coastal lines from storms and waves. The process of coral reef restoration is complex. Corals grow only a few centimeters per year, and any change in the surrounding environment can affect their ability to recover. Additionally, the salinization of agricultural lands became another serious problem. As a result of the tsunami, vast volumes of seawater flooded fertile soils, leading to a decrease in the yield of rice and other crops in countries like Sri Lanka and Myanmar. According to FAO, in 2005, more than 200,000 hectares of agricultural land were affected by salt deposits, requiring the use of special technologies to improve soil quality. The landscape changes after the catastrophe were significant. In some places, the shores became steeper, while in others, new shallow waters and lagoons formed. As a result, many animal and plant species that previously inhabited these ecosystems were forced to adapt to new conditions or migrate to other regions. However, nature, as practice shows, is capable of self-restoration. In some areas, a slow return of life began. New plants appeared, gradually replacing the lost species. Research conducted in 2010 showed that in some regions, fish populations were increasing, which may indicate the restoration of marine ecosystems. Nevertheless, full recovery will require not one decade, and ecologists continue to closely monitor changes in ecosystems to understand what measures are necessary for their protection and restoration. The restoration of mangrove forests and coral reefs, as well as the improvement of the condition of agricultural lands, remain in the focus of researchers and governments of affected countries. Palaco tsunamis are ancient tsunamis that have left significant traces in the geological record, allowing scientists to study their nature and consequences. Geologists study the deposits formed by these catastrophic waves to understand how often and with what force such events occurred. In particular, the study of deposits left by paleo-tsunamis includes the analysis of layers of sediment that may contain marine organisms such as shells and corals, as well as specific minerals transported by water. For example, in 2003, a group of geologists led by Dr. Christopher Snyder of the University of Washington State discovered paleo-tsunamis in the Cascadia Bay area, where they found layers of sand up to 1 meter high, indicating powerful waves resulting from earthquakes on the ocean floor. These deposits are typically located at significant depths beneath modern marine sediments, making them difficult to detect, but the use of radiocarbon dating and analysis of magnetic properties allows geologists to accurately determine the age of these layers. One notable example is the study conducted in 2009 on the coast of Japan, where scientists found evidence of paleo-tsunamis that occurred around 1,200 years ago, which helped assess the probability of future tsunamis in this region. These data help model the frequency and scale of potential tsunamis, which is crucial for developing early warning systems and preparing for natural disasters. Information about paleo-tsunamis can also be used to evaluate the resilience of coastal ecosystems, such as mangrove forests and coral reefs, which can play a protective role in mitigating the impacts of future disasters. Furthermore, the study of paleo-tsunamis contributes to understanding not only geological processes but also social dynamics, as history shows that such events can have devastating consequences for local communities and economies. For instance, the 1960s tsunami off the coast of Chile led to the creation of a system for monitoring seismic activity, which became an important step in risk management. Thus, the study of paleo-tsunamis allows us not only to look into the past, but also to prepare for future challenges that may arise due to climate change and the increase in frequency of extreme weather events. In 2020, the analysis of deposits in the Icelandic region revealed a series of significant paleo-tsunamis, indicating the need to reassess existing risk models in this area. Data collected from such research can be incorporated into modern models that predict the possible consequences of climate change, such as sea level rise and increased frequency of storms. Earthquakes are sudden and powerful underground shocks caused by the abrupt displacement of blocks of Earth's crust due to the accumulation of tension in tectonic plates. These plates, composed of rigid structures, float on viscous mantle fluid and can move at various speeds, ranging from several millimeters to several centimeters per year. When tension reaches a critical point, there is a sudden release of energy, resulting in the formation of seismic waves. These waves can spread in various directions, reaching the Earth's surface and causing vibrations that are felt as earthquakes. There are several types of seismic waves: primary P waves, secondary S waves, and surface waves. P waves travel faster and are longitudinal waves that compress and decompress, moving particles of material in the same direction as the wave. S waves travel more slowly and create transverse oscillations, moving only through solid materials. Surface waves, which reach the surface last, cause the most destructive effects because they generate complex oscillations that affect the ground and structures. These waves can cause strong vibrations that can destroy buildings, bridges, and other constructions. At high levels of energy released during an earthquake, significant damage can occur. For example, during the 1994 Northridge earthquake in Los Angeles, the magnitude of the shock was around 6.5 on the Richter scale, leading to the destruction of thousands of buildings and numerous human casualties. Earthquakes can occur at any time and in any place, making them highly unpredictable. They can happen in areas previously considered safe, such as the centers of continents, far from tectonic boundaries. This makes them particularly dangerous for those who are not prepared for such sudden events. Various methods of measuring and predicting earthquakes exist, but none can guarantee 100% accuracy. Modern scientists, such as seismologists and geologists, continue to study the mechanisms of earthquake formation and their consequences to minimize potential damage. The challenge in predicting earthquakes lies in the fact that even small changes in tension in the Earth's crust can lead to significant consequences. Scientific research shows that despite the availability of technologies capable of detecting small seismic activities, it is still impossible to accurately predict the exact time and location of the next major earthquake. This makes preparation and public education a crucial strategy for reducing the impact of earthquakes. Therefore, the mechanisms behind earthquakes remain a mystery to science, and these events can occur at any moment, making them one of the most dangerous natural phenomena. In 1930, in Chicago, as a result of an earthquake that occurred far from active tectonic boundaries, shocks were registered that were felt over a distance of more than 300 kilometers. The Great Lisbon Disaster of 1755 left an indelible mark on the history of Europe. This earthquake, which occurred on November 5th, had a magnitude of around 8 on the Richter scale and was one of the most powerful recorded in history. The epicenter was located in the Atlantic Ocean, near the coast of Portugal. The disaster resulted in catastrophic destruction in Lisbon. Around 18,000 buildings collapsed, including the famous Church of St. Nicholas and the Royal Palace. The city's streets were filled with debris, and as a result of the collapse of buildings, between 30 and 100,000 people lost their lives. But this was only the beginning of the calamities that befell the city. Soon after the initial tremors, a devastating tsunami struck, raising waves up to 20 meters high and crashing onto the shore, taking the lives of thousands and leaving behind only devastation. Water flooded many areas of Lisbon, and in combination with the subsequent fires that broke out due to the earthquake, this led to the complete destruction of the city's central part. The fires raged for several days, destroying the remaining structures and exacerbating the suffering of the survivors. This catastrophic event shocked not only the Portuguese but all of Europe. Philosophers and scientists began to actively discuss the nature of evil and divine providence, questioning why such a terrible event had befallen a Christian nation. In this context, the renowned philosopher Voltaire, condemning the cruelty of fate, raised questions about the meaning of suffering and how people should react to such disasters in his famous work, Candide. The Lisbon earthquake served as a catalyst for the development of seismology as a science. Scientists began to study the causes of earthquakes, their consequences, and methods of prediction. The 18th century was a time when scientists such as the Italian seismologist Giovanni Vincenzo and the Swiss physicist Gottfried Wilhelm Leibniz began to systematically observe and develop theories explaining tectonic processes. As a result of these efforts, the foundation for modern seismic research was laid. There even exist documents showing that after the Lisbon earthquake in the 18th century, the first seismographs were created in Europe, which helped to record tremors. Scientists began to realize the importance of preparing for such disasters and the necessity of creating warning systems. Thus, the events of November 5th, 1755, not only destroyed Lisbon, but also changed humanity's approach to understanding the nature of earthquakes and their impact on society. The concept established as a result of the catastrophe that natural phenomena can be linked to human suffering opened a new chapter in the history of philosophical thought and scientific analysis. In the night from April 21st to 22nd, 1906, a devastating earthquake struck San Francisco, caused by movement along the San Andreas Fault. The force of the shocks reached 8 on the Richter scale and lasted for about a minute, destroying buildings and bridges that were just beginning to gain popularity at the start of the 20th century. Panic erupted on the city's streets as people rushed out of their homes, leaving behind all their belongings, including their loved ones, in a desperate attempt to escape the unknown force of nature. The wooden structures that dominated the architecture of the time could not withstand the earthquake's force. More than 3,000 buildings were completely destroyed, and another 7,000 suffered serious damage. The most affected areas, such as Nob Hill and the financial district, were reduced to ruins, with streets littered with debris and rubble. However, the real hell began later when destructive fires broke out due to damaged gas pipes and stoves. The flames engulfed the city, turning it into an ocean of fire that mercilessly consumed everything in its path. Firefighters who tried to stop the spread of the fire faced a harsh reality. A lack of water and destroyed communications made it impossible for them to effectively fight this natural disaster. Hundreds of people who survived the earthquake perished in the inferno that raged for several days. Estimates suggest that the fire destroyed more than 25,000 buildings, leaving behind only ashes and ruins. The death toll was around 13,000, and hundreds of thousands of people left homeless were forced to live on the streets in tents and on makeshift camps set up in parks and city squares. Horrifying scenes of chaos unfolded. People searched for their loved ones. Some in despair tried to save their belongings, while others simply tried to survive in the midst of complete destruction and uncertainty. The San Francisco government, in a state of panic, tried to provide assistance to the victims, but the scale of the disaster left even the most experienced officials at a loss. A crucial aspect of the catastrophe was the realization that the city, built on a fault line, was not protected from recurring earthquakes. According to geologists, the San Andreas Fault is one of the most active in the world, and the event that occurred in 1906 was just one in a long chain of destructive natural disasters. Despite all efforts to restore the city, San Francisco would never return to its former appearance, and its residents were forced to learn to live with the constant threat posed not only by earthquakes, but also by the aftermath of these disasters. Seismic-resistant construction has become a necessity for many cities located in seismically active areas, such as San Francisco. Engineers and architects have been actively developing new methods and technologies to create buildings that can withstand earthquakes. For instance, in the late 1970s in Japan, systems of dampening were introduced that can absorb the energy generated by earthquakes. A notable example is the Tokyo Sky Tower, built using such technologies. Engineers added special dampeners that, like giant springs, can smooth out the building's oscillations. As a result, even during a strong earthquake, the building remains intact and is not destroyed. In the early 2000s, scientists from the University of Berkeley developed a method of flexible construction that allows buildings to bend during an earthquake, reducing the risk of damage. This technology is based on the use of flexible materials that can deform but not break. Blocks made of lightweight composite materials, such as carbon fibers, provide additional strength without increasing the weight of the structure. For example, in 2003 in Chile, a residential high-rise was built using such technologies and demonstrated its effectiveness during the earthquake in 2005. Architects also began using special building shapes, such as ovals and circles, which are less prone to damage in conditions of seismic activity. It is worth noting that in 2006 in Nepal, a program was implemented to assess the seismic resistance of old buildings, where experts recommended using principles based on traditional construction methods adapted to modern requirements. In addition to this, software for modeling seismic effects has become an integral part of design. Engineers can now simulate how a building will behave during an earthquake, allowing them to optimize the structure and reduce risks. For example, building designers in California use programs like SAP 2000, which allow for the analysis of the behavior of multi-story buildings under various seismic waves. Furthermore, to enhance the resilience of buildings, innovative materials such as high-strength concretes and high-plasticity steel are being used, which significantly extend the lifespan of structures. The Tokyo Institute of Seismic-Resistant Design is actively researching a new generation of concrete mixtures that can adapt to temperature and humidity changes, making them more resistant to deformations. It is also important to mention the role of standardization in seismic-resistant construction. In 2008, international organizations such as ISO and ASCE developed new design standards for seismic-resistant buildings, which became mandatory for use in countries with high levels of seismic activity. No less significant is the experience of countries such as New Zealand, where after the devastating earthquake in 2011, the entire system of seismic norms and regulations was revised. As a result, new buildings in Christchurch became not only more resistant to earthquakes, but also more comfortable for living. Systems for monitoring the condition of buildings, such as smart structure technology, allow for real-time tracking of changes in the structure, helping to prevent potential threats. Modern technologies in seismic-resistant construction are capable not only of protecting people, but also of preserving cultural heritage. Early warning systems for earthquakes play a crucial role in saving lives by providing people with the opportunity to take shelter in safe places before destructive waves arrive. Several highly effective seismic networks consisting of thousands of seismometers are in operation worldwide. For instance, Japan, known for its frequent earthquakes, has one of the most advanced systems, with over 3,000 seismometers distributed across the country. These instruments detect even the slightest tremors and transmit data in real time to the Seismic Information Management Center. The data processing algorithms used in these systems can analyze incoming information within seconds. When a seismograph detects an earthquake, the algorithms immediately calculate its magnitude and epicenter, allowing for an assessment of potential risk. For example, the Shake Alert system in California can warn residents about an impending earthquake up to several tens of seconds before it reaches their location. While this time may seem insignificant, it can be decisive for saving lives. Alerts are delivered through various channels: SMS notifications, mobile apps, radio, and television broadcasts. In Japan, for instance, the J-Alert system automatically sends messages to mobile phones and activates special signals on public transportation and in buildings. Additionally, loudspeakers in public places broadcast warnings, helping people to quickly respond to the threat. Such systems have already saved numerous lives, as the time they provide allows people to take refuge in safe zones or take precautionary measures. 80% of earthquake fatalities occur due to falling objects and building collapses, and early warnings can prevent most of these tragedies. In some regions, such as Chile, where a powerful earthquake of magnitude 8.2 struck in 2017, the early warning system gave people around 30 seconds to react. These seconds allowed many residents to evacuate to safe areas, significantly reducing the number of casualties. Investments in such technologies are always justified, as every second counts when the earth starts to shake. Early warning systems continue to evolve, adapting to new challenges and improving data processing algorithms to ensure the most effective population warnings. In Japan, a system has been developed that takes into account not only the magnitude, but also the type of earthquake, allowing for more accurate predictions of potential damage. Research shows that such technologies can significantly reduce economic losses from natural disasters. For example, in California, it is estimated that every dollar invested in the system can save up to $6 in post-earthquake recovery. Continuous improvements and innovations in this field demonstrate that modern technologies are not only capable of responding to threats, but also of preventing catastrophes and saving lives. Early warning systems for earthquakes are becoming increasingly important and accessible for countries at risk of seismic activity, and their implementation can ensure the safety of millions of people. The climate of Earth has undergone numerous changes throughout its geological history, with these changes often being quite radical. Over millions of years, the planet transitioned between various climatic states, from warm greenhouse periods with high temperatures to harsh ice periods with low temperatures, epochs when vast polar ice caps covered significant territories. For instance, during the period known as the Paleocene, the average temperature on Earth was significantly higher than it is today, and Arctic regions were ice-free. This facilitated the development of tropical vegetation, even in areas now covered by permafrost. There are many factors contributing to these changes: plate tectonics, volcanic activity, changes in solar radiation, and even orbital fluctuations of Earth. These processes could lead to atmospheric carbon dioxide concentrations exceeding modern levels by several times, causing global warming. Over millions of years, Earth experienced fluctuations in its atmospheric composition, reflecting not only geological events but also biological changes. For example, at certain points in history, the level of carbon dioxide could exceed 800 parts per million, significantly contributing to temperature increases and ecosystem changes. Meanwhile, during other epochs, such as the Pleistocene, Earth entered ice ages when glaciers covered significant parts of North America and Europe, reaching even the latitude of New York. During these times, sea level dropped, and continents appeared quite different from today. All these changes occurred cyclically, and the Earth's climate system has always demonstrated its variability. It is important to note that such changes occurred not only over millions of years, but also within shorter time frames, when the climate could change by tens or hundreds of degrees Celsius over just a few thousand years. These fluctuations have influenced species migration, changes in flora and fauna, and the development of human civilization. Research shows that even small temperature changes can have a significant impact on ecosystems, which we can observe today. Data indicate that over the last 100 years, the average temperature on Earth has increased by 1 degree Celsius, already leading to significant changes in weather conditions and sea level. These facts underscore that the Earth's climate system is dynamic and constantly changing, and throughout its history, it has never remained static, but has always been in a state of movement and transformation. The Paleocene-Eocene thermal maximum, which occurred around 56 million years ago, was one of the most significant climatic events in Earth's history. During this period, the surface temperature of the ocean rose by 5 to 8 degrees Celsius, leading to profound changes in ecosystems both on land and in water. This rapid warming was likely caused by emissions of carbon dioxide and methane resulting from volcanic activity and other natural processes. According to geologists, the level of carbon dioxide in the atmosphere reached up to 2,000 parts per million, which is 2 to 3 times higher than current levels. Such temperature changes led to a global rise in sea level of more than 20 meters, flooding extensive coastal areas and altering the planet's landscape. Marine ecosystems experienced significant stress, leading to major shifts in biodiversity. For example, coral reefs, which were home to numerous marine species, began to struggle with maintaining their structure due to the increase in water temperature and ocean acidity. In response to these changes, some coral species, such as Acropora, began to migrate to cooler waters, significantly altering their usual habitats. Meanwhile, in these warm waters, organisms like squid and various fish species thrived and adapted to the new conditions. On land, the temperature changes also favored the growth of tropical forests in areas where temperate ecosystems had previously existed. For instance, in North America and Europe, there was a mass spread of plants like palms and magnolias that could not previously grow in these latitudes. Scientific research indicates that even in the Arctic, forests existed during this time, and the climate was warm enough that tropical tree species could be found across the current territory of Canada. While many species, such as dinosaurs, had already gone extinct, mammals began to actively evolve and adapt to the new conditions, leading to the appearance of numerous new species. By the end of the Paleocene-Eocene thermal maximum, around 30% of all species on Earth had adapted to the new climate, indicating a high degree of ecosystem flexibility. This period also served as a precursor to subsequent climate change, as temperatures began to gradually decrease. The impact of the Paleocene-Eocene thermal maximum can still be seen today in various forms of life. For example, some modern tropical plants continue to retain their ancestral characteristics, indicating that they survived in conditions where temperatures were significantly higher than they are now. Data on the Paleocene-Eocene thermal maximum helps us better understand how ecosystems can respond to rapid climate change. In particular, some researchers, such as Dr. Emily Bennett from the University of California, argue that studying this period is key to understanding contemporary climate changes and their potential impact on biodiversity. This information is crucial given the current rates of climate change, which could lead to similar catastrophic consequences for ecosystems in the future. For instance, we can already observe species migration and changes in habitat ranges as a result of global warming. The Paleocene-Eocene thermal maximum remains an important object of study because it demonstrates how ecosystems can adapt to extreme conditions. For example, analysis of fossils shows that many groups of organisms, such as insects and mammals, were able to quickly evolve in response to changes in their habitat. This period provides a unique opportunity for scientists to understand how the biosphere responds to climate change and which species may be most vulnerable in the future. Comparing it with current rates of climate change underscores that despite the high adaptability of nature, ecosystems may face serious challenges if changes occur too rapidly. The Paleocene-Eocene thermal maximum occurred approximately 60 to 52 million years ago, and one of the main causes of this event was the massive release of methane from methane hydrates located on the ocean floor. Methane hydrates are crystalline structures composed of water and methane, which stabilize under high pressure and low temperatures, making them widespread on the ocean floor. Under conditions of temperature increase even by a few degrees, these crystals can begin to decompose, releasing methane into the atmosphere. Since methane is a powerful greenhouse gas, its increase in the atmosphere contributed to further warming. Research indicates that during this time, ocean temperatures could rise by 6 to 9 degrees Celsius over just a few thousand years, which in turn led to further methane release. Scientists like Dr. Klaus Huber from the University of Florida point out that such releases could have occurred due to tectonic activity or changes in sea level, which disrupted the stability of methane hydrates. As temperature increased, this triggered a chain reaction. Released methane contributed to further warming, which in turn led to new methane releases. In addition to methane, this period also saw an increase in carbon dioxide. Oceans were no longer able to absorb carbon dioxide as effectively as before, further exacerbating the problem. As a result of this process, Earth's temperatures reached record levels and the climate system became destabilized. Scientific data show that the level of carbon dioxide in the atmosphere during this time could reach values around 1,000 parts per million, which is 2 to 3 times higher than current levels. An important aspect of this period was its ecological consequences. Climate change led to mass extinctions, particularly among marine organisms. For example, coral reefs, which could not adapt to such rapid temperature fluctuations, began to disappear, negatively impacting ecosystems that depended on them. According to paleontologists, the diversity of marine life significantly decreased. According to research conducted by Dr. Daniel Lyer from the University of California, the thermal maximum led to significant changes in the composition of flora and fauna. New species adapted to high temperatures emerged, while others were on the brink of extinction. Ultimately, this period became not only a time of climate change, but also a crucial turning point in the evolution of life on Earth. Thus, the Paleocene-Eocene thermal maximum is a vivid example of how temperature changes can lead to chain reactions in ecosystems and cause global climate changes that continue to affect the biosphere. It is important to remember that similar catastrophes have occurred in Earth's history, and contemporary research helps us better understand how such events can influence future climate. The temperature on Earth reached record levels during this period, as confirmed by fossil data and analyses of marine sediments. Glacial periods, known as Earth's snow, are hypothetical epochs in the history of our planet when glaciers covered almost the entire surface, including equatorial regions. These epochs occurred over the last billion years, with the most well-known period spanning from the 8th to the 6th million years ago, when the surface temperature of Earth significantly decreased. During this time, oceans froze almost to the equator, forming massive ice shields that extended from the poles to the equator. Research indicates that such glacial epochs could lead to global climate changes, causing a sharp reduction in photosynthesis. As a result, the level of carbon dioxide in the atmosphere decreased further, exacerbating the cold conditions. In such conditions, life on the planet survived only in isolated refuges such as hot springs and deep-sea hydrothermal vents, where high temperatures and minerals created suitable conditions for the existence of microorganisms. These ecosystems were isolated from the cold world that dominated the surface. For example, in hot springs like those in Yellowstone National Park, Unique bacteria that thrive at temperatures above 100 degrees Celsius can be found, which could have been the ancestors of many modern forms of life. The frozen oceans were covered with a thick layer of ice that could reach several kilometers in thickness, creating insurmountable barriers to the migration of marine organisms. On land, in the harsh climate, survival became an art form. Some plant species, such as mosses and lichens, managed to adapt to extreme conditions, using unique mechanisms to protect themselves from the cold. In such conditions, life persisted only in subglacial waters, where the temperature remained just above zero, and where rare fish and other organisms could inhabit. Scientists believe that during the Earth's snow period, the sea level dropped by several hundred meters, opening up new land areas, but also creating conditions for large-scale migrations of animals seeking survival. Research shows that after such glacial periods, a rapid warming occurred, allowing ecosystems to recover and develop, leading to a rapid increase in biodiversity. Thus, Earth's snow became a significant stage in the evolution of our planet, allowing many species to adapt to extreme changes. During this time, not only mosses and lichens, but also marine organisms that could survive in conditions of constant cold and darkness existed. It is interesting that it was in such conditions that the first multicellular organisms appeared, which became the basis for further evolution of life on Earth. Scientific data show that during glacial periods, the level of oxygen in the atmosphere could drop to 30% of modern levels, creating additional difficulties for survival. The ice shields that covered the planet reflected sunlight, slowing down the heating process and leading to cycles of glacial and interglacial periods. In the end, these changes created unique conditions for the formation of new ecosystems and biological species, which became the basis for life as we know it today. In the conditions when Earth was in a state of snowball Earth, volcanoes began to play a key role in climate change. Volcanic activity increased, especially during periods such as the late Pleistocene, when a significant amount of carbon dioxide and other greenhouse gases were released into the atmosphere. This occurred due to frequent volcanic eruptions, such as the Toba eruption in Indonesia, which around 80,000 years ago led to global cooling, but also contributed to the accumulation of gases in the atmosphere when activity decreased. Carbon dioxide, sulfur, and water vapor began to accumulate, creating a greenhouse effect that gradually altered climatic conditions. As volcanic gases became more concentrated, the greenhouse effect intensified and Earth's temperature began to rise. This process was dramatic. Ice sheets that previously covered large areas began to melt, releasing vast amounts of fresh water into the oceans. For example, around 20,000 years ago, when glaciers began to retreat, sea level rose by approximately 100 meters, changing coastal lines and ecosystems worldwide. Glaciers in Greenland and Antarctica began to lose mass, contributing to further temperature increases. Studies show that as a result of this melting, carbon trapped in permafrost was released into the atmosphere, enhancing the greenhouse effect. This mechanism can be observed today. The melting of permafrost in Siberia, for example, leads to the release of methane, which is 20 times more effective at trapping heat than carbon dioxide. With each decade, this process accelerates, and Earth's climate system transitions from a state of deep cold to tropical conditions that could lead to climatic catastrophes. Scientists have calculated that over the past 100 years, the planet's temperature has risen by 1 degree Celsius, the fastest rate of climate change in Earth's history. Thus, the dramatic transition from a frozen world to greenhouse conditions continues, and the consequences of this transition are felt in every corner of the planet. Scientific data show that the level of carbon dioxide in the atmosphere has reached a record of 398 parts per million, which has not been observed for the past 800,000 years. Mass extinction of animals and plants in the Anthropocene has become one of the most pressing ecological issues of the 21st century. Scientists assert that the current rate of species extinction is tens, and even hundreds of times higher than the natural background level, which is 1 species per million per year. Unlike previous mass extinctions, such as the Cretaceous-Paleogene extinction that wiped out the dinosaurs, today's extinction is primarily driven by human activity, destruction of natural habitats, hunting, pollution, and climate change. For instance, according to the International Union for Conservation of Nature, more than 30% of all amphibians, more than 20% of mammals, and more than 35% of marine organisms are threatened with extinction. A crucial aspect of this situation is that anthropogenic impact on nature occurs on a global scale. The 10th edition of the IUCN Red List recorded more than 30,000 species at risk. Deforestation for agriculture and urban development leads to the loss of ecosystems' natural resilience, which in turn creates a chain reaction affecting other species and their habitats. Every 3 seconds, a forest area the size of a football field disappears from the planet, resulting in a loss of biodiversity and disruption of ecosystem services such as pollination and water purification. Given that more than 7 billion people depend on the planet's resources, their impact on the environment is becoming increasingly destructive. For example, according to UN estimates, agriculture now occupies more than 30% of the Earth's surface and is the leading source of greenhouse gas emissions. Additionally, climate change driven by human activity is already altering the migration routes of many animals and plants, further stressing vulnerable ecosystems. In some cases, such as with coral reefs, the rate of change is so rapid that the system cannot adapt, and within a few decades, entire ecosystems can disappear. It is essential to understand that human impact on nature is so global and powerful that one species, Homo sapiens, has become the cause of an ecological transformation that affects the entire planet. Scientists predict that if current trends continue by the middle of the 21st century, up to 60% of all species on Earth could become extinct. The arrival of the first humans on the Australian continent was a catastrophic event for the local megafauna. Around 65,000 years ago, when Homo sapiens first crossed the maritime straits, they encountered a unique ecosystem inhabited by giant marsupials such as the megatherium, the largest lizards in the world reaching lengths of up to 7 meters, and giant kangaroos weighing up to 500 kilograms. The isolation of Australian fauna from other continents made it particularly vulnerable to the new predator, which turned out to be not just a threat, but also a catalyst for ecosystem change. Research conducted by Australian paleontologists shows that hunting and competition with humans were the main factors leading to the extinction of species such as Diprotodon, a giant marsupial that went extinct around 15,000 years ago, and birds like Genyornis reaching heights of up to 3 meters and weighing up to 60 kilograms. These herbivores played a crucial role in maintaining ecosystem balance, and their disappearance triggered a chain reaction of changes. Without large herbivores that consumed vegetation and facilitated its regeneration, there was a change in vegetation. In some regions, there was an active invasion of shrubs, which in turn altered natural fire regimes. The occurrence of more frequent and intense fires not only destroyed the remaining ecosystems, but also created new conditions for the survival of smaller species such as turtles and small marsupials, which, however, could not replace the functions lost by the large herbivores. This change also affected local ecosystems, where microclimate and soil conditions began to change due to the loss of large plant forms that in turn supported the diversity of other species. Incidentally, according to researchers' estimates, with the disappearance of megafauna, including large marsupials and giant birds, Australia lost up to 90% of its large terrestrial mammals. This event became a striking example of how human intervention can fundamentally alter the evolutionary path of an entire continent. The extinction of megafauna in Australia also sparked further changes in the culture of indigenous peoples, who adapted to the new conditions but were unable to prevent the loss of their natural habitat. The dodo, also known as the dronte, was a flightless bird that inhabited only the island of Mauritius. The first European explorers, such as the Portuguese, discovered the island in the 16th century, but it was the Dutch who began actively settling on Mauritius in the 17th century. The first description of this bird appeared in the works of the Dutch naturalist Adrian van Rennes, who mentioned it in his writings in the 16th century. The dodo reached a height of 1 meter and weighed between 8 and 12 kilograms. It was a helpless bird, without natural predators on its native island, making it vulnerable to new threats. After the arrival of Europeans, hunting dodos became popular. The birds were not afraid of people and were easily caught. Additionally, pigs, rats, and cats were introduced to the island, becoming the main enemies of the dodos, destroying their eggs and chicks. By the 18th century, less than 100 years after the island's discovery, the dodo was on the brink of extinction. The last mentions of these birds date back to the 17th century, when they were already nearly extinct. By the end of the 17th century, the dodo was officially considered extinct. This extinction served as a tragic illustration of human stupidity and the lack of understanding of the value of unique species, which could disappear in just a few years under the impact of hunting and habitat destruction. The famous naturalist and botanist Sir Joseph Banks, who travelled with Captain Cook, also expressed regret over the fate of the dodo, considering it a symbol of lost nature. The 18th century was an era when many species faced a similar fate, and the dodo became one of the first examples of an ecological catastrophe caused by human activity. The disappearance of the dodo served as a harbinger of many future ecological crises, which will be studied by scientists. This species, which did not even have time to establish itself in the ecosystem of the New World, became a victim of human short-sightedness and indifference. Since then, the dodo has remained a symbol of extinct species, reminding us of how quickly humans can destroy something that was never considered a threat. Considering all this, the dodo is not just an extinct bird, but an important lesson about the need to protect unique ecosystems. The last finds of the dodo, including its fossilized remains, have been studied by scientists over the centuries, and these finds continue to spark interest in the reasons for its extinction and the importance of preserving biodiversity. Modern methods of preserving endangered species include various captive breeding programs, genetic material cryopreservation, and ecosystem restoration. For instance, the captive breeding program for the black rhino, initiated in the 1990s, has increased their population from fewer than 400 individuals to more than 2,000. Scientists from the international organization WWF are actively working on the conservation of rare species such as the Amur tiger, which was on the brink of extinction in the early 2000s. Since the launch of the protection program in 2003, the tiger population in the wild has increased by almost 30%. Genetic material cryopreservation, which allows for the freezing of DNA samples, is another crucial tool in the fight against extinction. Leading research centers like Frozen Zoo in San Diego store samples from more than 90 species of animals, including those that have gone extinct in the wild. This provides the opportunity to restore populations in the future using advanced cloning and genetic engineering technologies. Ecosystem restoration requires a comprehensive approach, including habitat restoration and the reintroduction of extinct species. In 2000, a program to restore habitats for rare species such as the Tasmanian devil and the Tasmanian wolf was initiated in Australia. Scientists from the University of Tasmania are developing strategies aimed at ecosystem restoration to provide the necessary conditions for the survival of these animals. One of the most successful examples of reintroduction is the return of the American bison to its historical ranges, made possible by the efforts of organizations the Nature Conservancy and Buffalo Field Campaign, which have been working on restoring the bison population in Grand Teton National Park since 2010. Each bison can weigh up to 1 ton and plays a key role in the prairie ecosystem, contributing to the maintenance of biodiversity. Conservation programs are becoming increasingly important in the face of global climate change, which threatens the existence of many species. Scientists from Global Biodiversity Outlook assert that around 1 million species are at risk of extinction in the coming decades. Conservation and restoration programs must consider not only current threats, but also anticipate future changes in habitats. In 2000, within the framework of the Convention on Biological Diversity, a strategy for the period up to 2020 was adopted, aimed at reducing the rate of biodiversity loss. The importance of these efforts is confirmed by the fact that ecosystems that have retained their diversity are more resilient to climate change and diseases. The restoration of lost species and ecosystems is not just an ecological issue, but also a matter of our direct responsibility to future generations who should inherit a planet rich in living beings. Anthropogenic climate change is a complex process driven by human activity, leading to significant alterations in Earth's climate system. The primary mechanism behind this change is the enhancement of the greenhouse effect, which occurs due to the increase in concentrations of carbon dioxide and other greenhouse gases in the atmosphere. The 18th century marked the beginning of the Industrial Revolution, when large-scale burning of fossil fuels such as coal, oil, and natural gas began. This resulted in a sharp increase in carbon dioxide emissions, which, according to scientists, grew from approximately 280 parts per million at the end of the 19th century to more than 410 parts per million by the 20th century. Each of these increases in carbon dioxide concentration prevents sunlight from effectively escaping back into space, creating a sort of blanket around the planet, leading to its warming. This process is exacerbated by other greenhouse gases like methane and nitrous oxide, which also have high thermal capacity and significantly influence climate conditions. Methane, released as a result of agricultural activities and organic matter decomposition, is 20 times more effective as a greenhouse gas in the short term compared to carbon dioxide. Consequently, even a slight increase in the concentration of these gases in the atmosphere can lead to significant changes in global temperatures. Meanwhile, human activities accelerate natural climate processes such as glacier melting and sea level rise, further disrupting the climate system. For instance, according to the World Meteorological Organization, the average surface temperature of Earth has already risen by more than 1 degree Celsius compared to pre-industrial levels, serving as a worrying sign that the climate system is under pressure, like a spring ready to compress and release energy in the form of extreme weather events. As a result, an increasing number of countries are facing the consequences of climate change, including an increase in the frequency of hurricanes, droughts, and floods, threatening not only ecosystems but also the lives of millions of people. Each of these factors contributes to a growing sense of imbalance in the climate system, where familiar cycles become unreliable and future predictions become increasingly complex. Scientists continue to warn about the risks associated with anthropogenic climate change and the urgent need for measures to mitigate these impacts. It is important to note that these processes do not occur in isolation. They are interconnected and create cascading effects that can exacerbate existing problems such as resource scarcity and security threats. Scientific research indicates that without significant efforts to reduce greenhouse gas emissions, we may face climate conditions that are not only extreme but also unpredictable. Countries like Norway and Sweden have already begun actively transitioning to renewable energy sources such as wind and solar power to reduce dependence on fossil fuels and decrease their carbon footprint. The melting of Arctic ice has become one of the most striking and alarming consequences of global warming. According to the National Oceanic and Atmospheric Administration of the United States, by 2020, the area of sea ice in the Arctic Ocean had decreased by more than 60% compared to the middle of the 20th century. This reduction not only affects the thickness of the ice cover, which has on average dropped to less than 1 meter, but also changes the surface color. The white, reflective surface of the ice is replaced by the dark surface of open water. The light surface of the ice reflects up to 90% of solar radiation, while dark water absorbs up to 90%, leading to further warming. This process, known as positive feedback, exacerbates warming in the Arctic, creating a cycle that cannot be ignored. Each year, the temperature in the Arctic is rising faster than in the rest of the world, and according to the Intergovernmental Panel on Climate Change, by 2050, the temperature could increase by 6 degrees Celsius. This change in ecosystems affects local species such as polar bears and seals, which depend on ice for hunting and reproduction. The reduction in sea ice threatens their existence as seals and bears lose their usual habitats. In addition, indigenous peoples such as the Inuit, who depend on hunting and fishing, face changes in the conditions of their traditional way of life. According to a study conducted by the University of Alberta in 2019, changes in the ecosystem lead to a decrease in the number of traditional food resources such as fish and seals, which puts the food security of these communities at risk. These changes do not affect only ecosystems, they also affect climate systems, exacerbating extreme weather events. For example, in 2009, record temperatures were observed in Siberia, caused by changes in Arctic circulation related to global warming. This leads to the fact that such anomalies become more frequent and intense. Against the backdrop of melting glaciers and climate change, sea level is also beginning to rise, threatening coastal territories and island states. By 2080, the sea level is expected to rise by 1 meter, which will have a significant impact on millions of people living in low-lying coastal areas. The complexity of the situation is exacerbated by the fact that many of these changes occur so rapidly that the scientific community does not have enough time to adequately assess and adapt to the new realities. The melting of Arctic ice not only changes the climate picture of the planet, but also puts the existence of entire ecosystems and cultural traditions of indigenous peoples at risk, which requires urgent measures to minimize the consequences of this process. The melting of the Greenland and Antarctic ice sheets has become one of the most pressing issues facing the planet today. The Greenland ice sheet, which covers an area of around 1 million square kilometers and contains approximately 7 meters of sea level rise, is losing stability each year. According to a study conducted in 2020 by a group of scientists from the University of Copenhagen, the rate of ice melt in Greenland has increased from 31 billion tons per year in the 2000s to 131 billion tons per year by 2018. This means that the flow of glaciers, such as the Jakobshavn Glacier, which moves at a speed of up to 15 kilometers per year, is becoming increasingly intense. Scientists are observing that glaciers once considered stable are now rapidly losing their mass into the ocean. The situation in Antarctica is no less dramatic. According to NASA, the rate of melting in West Antarctica has significantly increased. In particular, the Totten Glacier, one of the largest in this region, has been losing ice at a record pace, threatening entire ecosystems and coastal areas at risk of flooding. In 2009, a group of researchers led by Dr. Eric Rignot discovered that warm ocean currents are accelerating the melting process, undermining ice shelves and contributing to the formation of giant icebergs. As a result of these processes, in 2020, scientists recorded the calving of an iceberg with an area of more than 1,000 square kilometers from the Larsen C ice shelf in Antarctica. This phenomenon, known as active calving, occurs when the pressure of water beneath the ice shelf becomes too high and the ice can no longer hold its mass. As a result, colossal icebergs are formed, which then drift in the ocean, raising sea levels and threatening coastal regions. In recent years, there has been an increase in such events. In 2015, an iceberg with an area of nearly 300 square kilometers calved from the Brumstorf Glacier. All this creates an atmosphere of slow but inexorable transformation of polar regions, contributing to global consequences that will be felt in the future. Research shows that if current trends continue, sea levels could rise by more than 1 meter by the end of the century, affecting millions of people in coastal areas. Scientific data underscore that the feedback loop between ice melt and climate change is strengthening, and this requires immediate measures to mitigate the consequences. Glaciers on the planet are not just static masses of ice. They are dynamic systems that respond to temperature and sea level changes. 80% of the ice sheets in Greenland and Antarctica are in a state of constant movement, indicating that this is not just a local but a global problem requiring close attention. As the temperature on the planet rises, the level of the world ocean continues to increase, leading to serious consequences for low-lying coastal areas. There are two main mechanisms contributing to this process: the melting of glaciers and thermal expansion of water. According to the Intergovernmental Panel on Climate Change, the ocean level has risen by more than 20 centimeters since the end of the 19th century, and if current trends continue, by the end of the 21st century, it could rise by 1 meter or more. This would flood extensive areas, including many coastal cities and island states, which are already at risk. For example, in Bangladesh, where 80% of the territory is located less than 10 meters above sea level, millions of people may become refugees due to the rise in sea level. In the Pacific Ocean, countries like Tuvalu and Kiribati face the threat of complete inundation, which calls into question their existence as sovereign states. Adaptation of infrastructure becomes a critically important task. It is necessary to build protective dams, develop early warning systems, and review urban planning standards. For instance, in the Netherlands, where a large part of the territory is below sea level, technologies such as floating houses and reinforced shores are actively used to cope with potential floods. However, it is also important not to forget about social aspects. Migration from flooded areas is already occurring, and it is predicted that by the 2000s, on a global scale, this will become one of the most acute problems of mass displacement. An example is the internal displacement of people in Mali, where due to climate change, people are leaving their homes in search of safer places to live. The vulnerability of coastal cities is becoming increasingly apparent as they face a combination of growing threats: hurricanes, floods, and coastal erosion. Existing infrastructure systems often cannot withstand the new climate conditions, highlighting the need for a comprehensive approach to planning and preparation for possible disasters. Experts estimate that the total economic losses from sea level rise could reach trillions of dollars, indicating the need for immediate action to mitigate the consequences. For example, in the United States alone, in New York City, it is necessary to invest more than $100 billion in flood protection and improvement of the resilience of urban infrastructure. Moreover, experts emphasize that the rate of sea level rise will vary by region. In some places, such as the eastern seaboard of the United States, the level may rise faster due to the characteristics of ocean currents and tectonic activity. This creates additional challenges for local authorities and residents who must adapt to changing conditions. Ultimately, climate change caused by human activity requires a comprehensive understanding of the problem and action at all levels, from local to international. Changes in precipitation patterns due to global warming are becoming increasingly evident and have serious consequences for ecosystems and human activities. The global warming model predicts an increase in the frequency and intensity of extreme weather events. According to the Intergovernmental Panel on Climate Change, in the 21st century, the number of heavy rainfall events in some regions of the world will increase by 30%. This means that areas previously experiencing moderate rainfall may now be subject to devastating floods. For example, in India in 2020, heavy rains led to the flooding of over 200,000 hectares of agricultural land, resulting in significant losses and a food crisis. Meanwhile, other regions, such as the southern United States, are facing longer and more intense droughts. Research shows that in some parts of California, rainfall levels could decrease by 25% by the end of the 21st century, leading to faster depletion of water resources than they can be replenished. This creates significant challenges for farmers who cannot rely on traditional irrigation methods. For instance, in 2019, farmers in California turned to innovative methods such as drip irrigation to maximize the use of limited water supplies, but this requires substantial initial investments. The unpredictability of weather conditions puts traditional agricultural practices at risk and complicates planning. In Brazil, for example, farmers are now facing unexpected rainy and dry seasons, making crop yields unpredictable. As climate change continues to develop, new strategies are needed to adapt to this changing climate. Increased precipitation intensity also puts low-lying settlements at risk of flooding. In the Netherlands, where sea levels are rising, the government has already allocated billions of euros for the construction of protective dikes and water drainage systems. In such conditions, traditional urban planning methods become ineffective. In some African countries, for example, farmers are starting to use drought-resistant crop varieties to cope with increased droughts. Research shows that such varieties can reduce water demand by 30% and increase yields. However, these methods require time for implementation and adaptation. The complexity of the situation is exacerbated by the fact that global warming affects not only precipitation levels but also temperature, which in turn affects the rate of evaporation and water availability. For example, in Australia in 2017, record high temperatures led to a 30% increase in water evaporation from the soil, exacerbating the water deficit. This creates a vicious cycle where climate change leads to further deterioration of conditions for agriculture and infrastructure development. Ultimately, precipitation is becoming not only more intense but also less predictable, requiring society and authorities to adapt to these new and harsh living conditions. Climate change necessitates a rethinking of resource management approaches to minimize risks and enhance resilience to future climate challenges. Geoengineering represents a concept of deliberate human intervention in the Earth's climate system to counteract global warming. This idea emerged in response to the growing challenges posed by climate change and encompasses various approaches aimed at reducing the concentration of greenhouse gases in the atmosphere and regulating solar radiation. An example of such intervention could be the idea of adding particles to the stratosphere to reflect sunlight, but this is just one of many possible strategies. On the other hand, many scientists warn about the potential risks of such actions, as interfering with complex natural systems can lead to unpredictable consequences. Research shows that the Earth's temperature has already risen by 1 degree Celsius since the beginning of the industrial era, and if no decisive actions are taken, it could increase by 3 to 4 degrees by the end of the century, which would be a catastrophe for ecosystems and human society. Ethical and scientific questions related to geoengineering are becoming increasingly relevant. How to determine the boundaries of acceptable intervention, how to assess the consequences for human health and the environment. In the absence of clear answers, scientists and policymakers find themselves facing a difficult choice: continue observing the deterioration of the climate or risk launching technologies that could either save or destroy. Research shows that without actions to reduce carbon emissions, global temperature could reach critical levels, leading to mass migrations, resource shortages, and possible conflicts. At the same time, active actions may not only fail to solve the problem but also exacerbate it, creating new ecological challenges. Leading scientists such as Dr. Kevin Anderson of the University of Manchester emphasize that geoengineering should be considered as a complement, not a replacement, for traditional methods of reducing emissions. Estimates suggest that if no measures are taken besides active intervention, more than 1 billion people may face water scarcity by mid-century. The risks associated with inaction and the uncertainty caused by intervention create a vicious circle in which every decision becomes a burden. The complexity of the climate system requires a scientific approach that combines nature and technology, and each new initiative should undergo strict scrutiny. Current research indicates that geoengineering could become a necessary tool in the arsenal of methods to combat climate change, but only under strict control and risk assessment. In the 20th century, the average global temperature increase was only 1 degree, but this is already enough to cause significant changes in weather conditions and ecosystems. Spraying aerosols into the stratosphere is one of the technologies of geoengineering aimed at reducing global temperature, mimicking the effect created by large volcanic eruptions. 80,000 years ago, the Toba volcanic eruption in Indonesia led to global cooling, lowering the average temperature by several degrees for decades. This technology is based on spraying particles such as sulfur into the stratosphere, where they form clouds that can reflect part of the solar radiation back into space. For example, the Harvard Solar Geoengineering Research Program is studying the possibility of spraying aerosols using high-flying aircraft that can reach heights of up to 20 kilometers. These aircraft can spray aerosols into the stratosphere, creating the desired effect that could temporarily reduce global temperature by 1 to 2 degrees Celsius. However, such technologies are not without risks and side effects. Changes in the distribution of precipitation in different regions can lead to droughts in some parts of the world and floods in others. Research conducted at the University of California in Los Angeles shows that spraying aerosols can affect local climate conditions, which in turn can impact agriculture and water resources. Additionally, there is a risk of damaging the ozone layer, which protects the Earth from harmful ultraviolet radiation. Work done in the 20th century showed that the stratosphere contains approximately 250 billion tons of ozone, and any interference in this area can lead to unpredictable consequences. For instance, in the year 2000, scientists from the University of Michigan discovered that the use of aerosols can not only weaken the ozone layer but also cause its depletion in the troposphere, which must be taken into account when developing such programs. Despite the potential risks, some experts, such as Dr. Ken Caldeira, insist on conducting field tests to assess the real impact of such technologies on the climate and ecosystems. Currently, there are no clear international norms regulating the use of geoengineering, making this area particularly sensitive and requiring careful control. In 2019, the United Nations held a conference where these issues were discussed, emphasizing the need to develop ethical and scientific standards for climate intervention research. Within such research, it is important to consider all risks and potential benefits to avoid catastrophic consequences for the planet. Thus, technologies for spraying aerosols into the stratosphere open new horizons in the fight against climate change, but require serious scientific analysis and public discussion. The effectiveness and safety of these methods remain subjects of active debate and research, as many aspects are still not studied. Technologies for capturing and storing carbon represent one of the greatest technological challenges of our time, requiring the development of infrastructure comparable in scale to the oil industry. Direct capture of carbon dioxide from the atmosphere, known as direct air capture, DAC, has become a focus for scientists and investors since the early 2000s. For example, carbon engineering, founded in 2008, has developed a technology that uses chemical reactants to extract CO2 from the air. The process involves using large fans to pass atmospheric air through special solutions that bind carbon dioxide. According to carbon engineering, one installation can capture up to 1 million tons of CO2 per year, equivalent to the emissions of approximately 200,000 cars. However, to have a significant impact on the level of carbon dioxide in the atmosphere, thousands of such installations would need to be created worldwide. Carbon capture technology is not limited to atmospheric air. There are also methods that capture CO2 directly from industrial sources, such as power plants and factories that produce carbon emissions. For example, in 2019, an installation was opened in Iceland that captures CO2 from the atmosphere and stores it in underground geological formations. This process, known as carbon capture and storage, CCS, involves capturing carbon dioxide, compressing it, and injecting it into underground voids. The Climeworks installation in Iceland, named Orca, can capture up to 400 tons of CO2 per year using geothermal energy to reduce the carbon footprint of the process. However, for effective deployment of CCS technologies, a large-scale infrastructure would need to be created. Expert assessments show that to achieve global climate goals, at least 7 billion tons of CO2 would need to be captured and stored annually by mid-century. This would require not only significant investments, but also the creation of a network of pipelines for transporting carbon to storage sites, comparable in complexity to existing oil and gas infrastructure. Interestingly, if managed properly, captured carbon can be used as a resource, for example, for the production of synthetic fuels or in construction. In this context, companies like Carbon Clean Solutions are developing technologies that convert CO2 into useful products. However, critics point out the high cost of these technologies and the need for more significant efforts in reducing carbon emissions at the source. Research shows that at current carbon credit prices and high capture costs, many projects remain economically unfeasible without government support or a significant increase in carbon taxes. Therefore, the challenge before the world is not only to develop effective technologies, but also to create an economic model that makes them viable. Considering that carbon emissions continue to rise and climate changes become increasingly noticeable, the need for large-scale solutions for capturing and storing carbon becomes critically important. In 2023, the International Energy Agency emphasizes that without active use of CCS technologies, achieving the set climate goals is impossible. Healthy ecosystems, such as forests, wetlands, and marine ecosystems, play a crucial role in carbon sequestration, acting as natural carbon sinks. For instance, forests absorb carbon dioxide through photosynthesis, with each hectare of tropical forest capable of absorbing up to 18 tons of carbon per year. Studies conducted in 2020 in the Amazon rainforest demonstrated that intact forests can accumulate carbon in their trees and soils, making them one of the most effective solutions for combating climate change. According to the World Wildlife Fund, reforestation and afforestation could increase biomass by 10 billion tons of carbon by 2030. Wetlands, on the other hand, store carbon in their organic soil, which accumulates over thousands of years. Research conducted in 2018 showed that restoring 1 hectare of wetland can retain up to 40 tons of carbon. Additionally, wetlands not only absorb carbon but also filter water, improving water quality and preventing floods. Marine ecosystems, including mangrove forests and seagrasses, also play a vital role in carbon sequestration. Mangrove forests, for example, can absorb carbon 10 times faster than tropical forests and can store carbon in their roots and sediments. Studies conducted in 2019 in the Bay of Bengal showed that mangrove forests can retain up to 6 billion tons of carbon. These ecosystems not only serve as carbon sinks but also provide essential services such as habitat for numerous species, coastal protection from erosion, and conditions for fisheries. Restoring these ecosystems has become a priority for many countries, as healthy ecosystems support biodiversity, regulate water regimes, and prevent soil erosion. For example, in 2020, Indonesia launched a program to restore 30% of lost mangrove forests, which not only improves the carbon balance, but also supports local communities dependent on fisheries. Restoring wetlands in Europe, particularly in Germany and the Netherlands, has also become a key part of strategies to reduce carbon emissions. In 2020, more than 100,000 hectares were restored, which will help retain around 5 million tons of carbon. These examples illustrate how targeted restoration of natural ecosystems can significantly contribute to carbon sequestration while also improving the state of the environment. In the vicinity of Earth, there are millions of objects that pose potential threats to our planet. These objects, known as asteroids and comets, vary in size from small pebbles to massive bodies tens of kilometers wide. For instance, according to NASA estimates, there are more than 7,000 known asteroids in our solar system whose orbits intersect with Earth's path. Each year, Earth encounters numerous small meteoroids, many of which burn up in the atmosphere, creating spectacular meteor showers. However, larger objects can pose a real danger. In 1989, an asteroid larger than 30 meters fell in Siberia, causing an explosion equivalent to the detonation of dozens of atomic bombs. Such events underscore the constant dynamic in space, where our planet moves among potential threats, and even small objects can cause significant damage upon impact. About 60% of known asteroids with orbits that intersect with Earth's orbit were discovered only in the last few decades, raising questions about how many more objects may be hidden in the depths of space. Scientists and astronomers around the world monitor these objects to predict their trajectories and prevent possible collision. In 2019, a project was launched to track and study so-called potentially hazardous asteroids that may approach Earth within 2 million kilometers. It is important to understand that even minor changes in the orbit of such objects can lead to catastrophic consequences. For example, an asteroid just 300 meters in diameter, if it collides with Earth, could cause destruction within a radius of more than 100 kilometers. Additionally, according to specialists' estimates, about 30 tons of cosmic material falls on Earth each year, and this is only officially registered data. Thus, our planet exists in a state of constant cosmic vulnerability, and despite scientific and technological advancements, the level of threat remains high. Astrophysicists continue to conduct research to understand the composition and structure of these cosmic objects to better predict their behavior. Programs for detecting and tracking asteroids are becoming increasingly relevant, as early detection is crucial for taking measures to protect the planet. One such measure is the creation of a warning system that allows assessing risks and developing possible strategies to deflect threatening objects several months before a potential collision. Research shows that even minor manipulations with asteroid orbits can significantly alter their course. Various methods are being developed for this purpose, including the use of nuclear charges and gravitational tractors that could deflect an asteroid from its dangerous path. The scientific community actively discusses these issues, and each new discovery in astronomy underscores the importance of being prepared for asteroid danger. Thus, the cosmos we inhabit is full of mysteries and hidden threats, and understanding these risks is a necessary step to ensure the safety of future generations. Astronomers are actively engaged in the discovery and cataloguing of near-Earth objects, utilizing powerful telescopes and specialized algorithms. One of the most well-known projects in this field is the Pan-STARRS program, launched in Hawaii in 2012. The Pan-STARRS telescope can detect objects up to 30 meters in size, located at distances up to 100 million kilometers from Earth. Astronomers systematically scan the sky, studying it in various light spectra, including visible, infrared, and ultraviolet, which allows them to identify both asteroids and comets. One of the key aspects of astronomers' work is the creation of algorithms that process data from telescopes to automatically detect moving objects. These algorithms analyze images of the sky, comparing them with databases to determine which objects are moving relative to background stars. For example, the NEOWISE program, launched by NASA in 2009, uses infrared data to detect and characterize small bodies in the solar system, which helps improve our understanding of their composition and structure. Each discovered body requires a thorough assessment of its orbit. For this, astronomers use methods based on calculating the motion parameters of the object, using observations at different stages of its trajectory. These calculations help predict the object's future movement and assess its potential danger to Earth. If an object approaches our planet, astronomers classify it on the Torino scale, which ranges from 0 to 10. 0 indicates no threat, while 10 signifies an inevitable impact. For instance, the asteroid Apophis, discovered in 2004, was initially rated at 4, but after refining the calculations, its rating was lowered to 0. International cooperation plays a significant role in the discovery and monitoring of near-Earth objects. Organizations such as the European Space Agency and the ISS actively exchange data and work on common projects. The Arecibo program, launched in 1961 in Puerto Rico, used a radio telescope to study asteroids and comets, making a significant contribution to understanding their physical properties. Currently, work is underway to improve observation technologies, including the use of satellites and ground-based observatories, which allows for more effective tracking of near-Earth objects. In 2020, the Rubin telescope was launched, which will be able to detect more than 30,000 objects each year, significantly enhancing our capabilities in planetary defense. Such efforts highlight the importance of being prepared for potential threats from cosmic objects and the need for continuous sky monitoring to ensure the safety of our planet. It is important to note that for effective tracking of near-Earth objects, it is necessary to consider not only their sizes and orbits, but also their potential collisions with Earth, which requires a comprehensive approach and the interaction of various scientific communities. The concept of protecting Earth from asteroid threats encompasses several potential methods, each with its own strengths and weaknesses. One of the most discussed approaches is the use of kinetic impactors. These devices are designed to alter the orbit of an asteroid by directing it towards Earth. For instance, in 2021, NASA launched the DART Double Asteroid Redirection Test mission, which involved a collision with the asteroid Dimorphos to test the effectiveness of this method. Scientists aim to change the orbit of an asteroid that is 10 times smaller than its larger companion. The collision occurred at such a speed that specialists could observe changes in the asteroid's orbit and confirm that kinetic impactors could be a viable method for redirecting asteroids. However, for this method to be successful, it is crucial to accurately estimate the time remaining until a potential collision to choose the optimal moment for impact. Another method that is actively being researched is the use of gravitational tractors. This technology involves a spacecraft that, by passing near an asteroid, gradually changes its orbit due to its gravitational pull. In the 21st century, scientists proposed various projects, including a concept of a spacecraft that would remain near an asteroid for several months or even years to gradually alter its trajectory. This method requires significant time but could be less destructive and more predictable. For example, the Gravity Tractor project was proposed in 2009, and its successful implementation could make it possible to protect against threats from large objects without the need for their destruction. It is also important not to overlook the use of nuclear explosions as one of the most radical methods. This approach involves using nuclear warheads to destroy or deflect an asteroid from its collision course with Earth. In the 1960s, the US government conducted experiments on this topic, including the NERVA project, which studied the possibility of using nuclear engines to create powerful impacts on asteroids. However, this method has several significant limitations, including potential radiation consequences and the need for precise calculation of the explosion's force to achieve the desired effect. In the 21st century, the concept of nuclear deflection was revisited as scientists began conducting simulations to understand how to effectively apply this method. Experts believe that the combination of these approaches could be the key to creating an effective system for protecting against asteroid threats. Technological advancements in space research and rocket technology open new horizons for humanity, allowing us not only to protect ourselves from cosmic threats, but also to actively participate in creating a safe, near-Earth environment. For example, numerous international organizations, including the European Space Agency, are actively working on developing global strategies for protecting our planet, including the creation of monitoring and early warning networks. The application of technologies such as artificial intelligence and big data can significantly enhance the effectiveness of predicting asteroid trajectories and their potential impact on Earth. Humanity has already made significant strides in this direction, and with each passing year, we are getting closer to the ability not only to observe cosmic threats, but also to actively prevent them. In 2023, a new mission to study near-Earth objects is expected to launch, aimed at improving our knowledge of potentially hazardous asteroids. International cooperation in the field of planetary defense is becoming increasingly relevant as the threat posed by asteroids and comets requires united efforts from countries around the world. In the 21st century, particularly after the incident in Chelyabinsk in 2013, when a meteor entered the atmosphere and caused significant damage, the need for coordination of observations and data exchange became apparent. One of the key projects is NASA's Planetary Defense Coordination Office program, established in 2014, which is responsible for identifying and tracking potentially dangerous objects. Within this program, NASA actively collaborates with the European Space Agency, ESA, and other organizations such as the Japan Aerospace Exploration Agency, JAXA, and Roscosmos, allowing the pooling of resources and technologies for more effective monitoring of cosmic threats. For example, in 2020, ESA launched the HERA project, which includes a mission to study the binary asteroid system Didymos, where it will work with NASA, conducting joint observations and data exchange on the results. At international forums such as the United Nations Conference on the Exploration and Use of Outer Space, countries discuss strategies for improving global monitoring and actions in case of threat detection. In 2018, a declaration on joint efforts in planetary defense was signed, involving more than 50 countries. This event underscores that the threat from space is a factor that unites humanity, regardless of political differences. One of the striking examples of such cooperation is the Asteroid Watch initiative, which allows users to track information about nearby asteroids and receive updates on new discoveries. This program is actively supported by both NASA and ESA, ensuring the availability of information for a wide audience and the scientific community. An important aspect is the creation of international standards for data exchange, which helps avoid duplication of efforts and increases the effectiveness of response to potential threats. Joint missions, such as NASA's Double Asteroid Redirection Test, DART, mission launched in 2020, serve as an example of how countries can work together to develop and test technologies that can alter the trajectory of an asteroid. This mission involves a collision with an asteroid in 2022, which will be the first test of technology for changing the course of celestial bodies. The success of this mission could form the basis for future strategies to protect Earth from asteroids. Thus, international cooperation in the field of planetary defense becomes an important element of global security, where each country contributes to the common cause. Threats from space highlight that the safety of the planet depends on a common understanding and unity of efforts, which requires countries to overcome political differences and focus on a single goal. Within this cooperation, in 2020, the International Asteroid Warning Network, IAWN, was created, serving as a platform for information exchange and coordination of actions between states and scientific institutions. This includes organizations such as NASA, ESA, and others working on the creation of an early warning system for potentially dangerous objects, which allows for advanced planning of possible actions. It is important to note that this cooperation not only strengthens security but also contributes to the development of new technologies and methods that can be used in other areas of science and technology. On Earth, tectonic plates are in constant motion, and this movement will ultimately lead to the formation of a new supercontinent. Scientific research shows that over the past 300 million years, Earth has experienced several cycles of continental union and separation, known as supercontinents. Currently, according to geological data, plates continue to move at an average speed of about 2 centimeters per year. This may seem like a slow process, but over tens of millions of years, this growth becomes significant. Over the next 100 million years, continents will continue to approach each other, and at some point they may reunite into a single whole. The union of continents occurs due to a series of tectonic processes, including subduction, when one plate descends under another, and the breakup of continents, which can lead to the formation of new oceans and new lands. For example, when Pangaea broke apart around 200 million years ago, the Atlantic and Indian Oceans were formed. There are various scenarios describing how a new supercontinent might look in the future. One such scenario is the convergence of the African and Eurasian plates, which could lead to the formation of a new continent covering a significant part of the land. It is important to note that this process will continue for millions of years, and humanity is unlikely to witness this event. From a geological perspective, our life on the planet is just a fleeting moment. Research shows that even after the disappearance of humanity, Earth will continue to evolve. Plates will collide, creating new mountain ranges, as happened with the Himalayas, which formed as a result of the collision of the Indian and Eurasian plates. Over the next 100 million years, as continents begin to approach each other, new reefs and volcanoes will form. Volcanic activity can lead to the emergence of new ecosystems inhabited by unique species adapted to changing conditions. This can also cause changes in climate, as new geographical forms will influence atmospheric flows and ocean currents. As history shows, Earth is a dynamic system where every movement of the plates has significance. If we look at a map of Earth through 200 million years, we can see a completely different planet where continents are located differently and form new lands. Plates will continue their movement, and eventually, through millions of years, we will see how our world changes again. Scientific models suggest that through 300 million years, we can expect the appearance of a huge supercontinent that will unite all existing lands. This process is called the supercontinent cycle, and it has occurred many times in the history of our planet. Underwater mountain ranges such as the Himalayas will continue to grow, and in the place of modern oceans, new lands may appear. Geologists study this phenomenon to understand how it can affect the future of our planet and its ecosystems. Research conducted by scientists such as David Lane and others shows how tectonic movements will continue, creating new forms of relief and changing climatic conditions. The tectonic cycle is not just a geological phenomenon, it is a continuous process that will occur even when humanity no longer exists. The model of the future supercontinent Pangaea Ultima suggests that the current continents will reunite into a single landmass in 250 million years. Geologists such as Dr. Martin Calypso from the University of California, Santa Barbara, envision this supercontinent to be mainly located in the southern hemisphere, stretching from the equator to the southern latitudes. Its shape, according to scientists, will resemble a giant shovel with a wide central mass and narrow edges facing the oceans. The center of Pangaea Ultima is likely to be a vast plain surrounded by mountains formed by the collision of tectonic plates. These mountain ranges will act as a barrier to moist oceanic winds, resulting in an extremely continental climate in the center of the supercontinent, with high temperatures and low rainfall, similar to modern deserts like the Sahara. In contrast, the coastal areas will have a milder climate with abundant moisture and a more diverse ecosystem, facilitating the growth of tropical forests and wet savannas. A key aspect of the model is that Pangaea Ultima will be in a zone where different climate zones converge, creating unique conditions for biodiversity and evolutionary processes. In this context, temperatures in the center of the supercontinent could reach over 50 degrees Celsius in summer months, while winters will be characterized by sharp cooling, leading to the formation of ice caps on its northern and southern edges. Scientists also predict that processes such as volcanism and earthquakes will be more active than ever, as tectonic plates continuously move and interact. One of the distinctive features of Pangaea Ultima is its isolation from the oceans, which will lead to unique development of flora and fauna, similar to what is observed on islands like the Galapagos. Research shows that in such conditions, new species adapted to extreme climatic conditions can emerge, creating a completely new ecological balance. As Pangaea Ultima forms, sea levels will fluctuate, adding further complexity to the formation of coastal lines. It is important to note that such changes will occur over millions of years, making it extremely difficult to predict all aspects of this process. However, based on calculations, by the time Pangaea Ultima forms, the land area will exceed 60 million square kilometers, significantly increasing the habitable territory on the planet. Scientists also suggest that the forming oceans, such as the New Tethys or World Ocean, will have a significant impact on the climate conditions of the entire planet, contributing to the formation of new meteorological patterns. On the supercontinent of the future, known as Pangaea Ultima, the climate will be characterized by extreme seasonal temperature fluctuations, making the interior regions practically uninhabitable. Scientific research indicates that at such latitudes as equatorial and tropical, temperatures can rise to 50 degrees Celsius in the summer months, while in winter they can drop to 0. This will result in sharp contrasts between different seasons, creating conditions where a large part of the land will become too dry and hot. The interior regions of the supercontinent will suffer from high temperatures and lack of rainfall, leading to aridity that can destroy vegetation and make life impossible for many animal species. For example, a study conducted in 2020 by scientists from the Institute of Climate Research at the University of Cambridge showed that such conditions are already observed in some regions of our planet, such as the Sahara, where the rainfall level is less than 200 millimeters per year. This transformation of climatic conditions will contribute to the formation of large deserts that will occupy significant areas of land. At the same time, the coasts of the supercontinent will be affected by monsoons, leading to a sharp increase in rainfall in these zones. Monsoons, acting over several months, can provide up to 3,000 millimeters of rainfall, creating humid tropical forests and rich ecosystems in coastal areas where biodiversity will be concentrated. Scientists suggest that such a concentration of life in coastal zones will lead to the formation of unique ecosystems with a high degree of adaptation to changing climatic conditions. Meanwhile, the interior areas may become dry deserts, where survival will be possible only for the most resilient and adapted species. For example, only those organisms that can survive long periods of drought and extreme temperatures will have a chance of survival. As a result, on the supercontinent of the future, we can expect that ecosystems will be divided into two sharply contrasting types: rich and diverse coastal zones where life will flourish, and barren interior regions where complex forms of life cannot exist. This may lead to a sharp reduction in biomes and, as a consequence, to the loss of many species that previously inhabited more favorable conditions. Some researchers, such as Dr. Emily Richardson from the University of Toronto, have already pointed out the possible consequences of such a division, including the rapid disappearance of species and a decrease in genetic diversity in the remaining populations. In the end, climate change on Pangaea Ultima may create a world where survival becomes an art and ecosystems are threatened with extinction. In the distant future, when humanity has vanished from the face of the Earth, ecosystems will begin to recover and adapt to new conditions. The disappearance of humans will open up numerous ecological niches that will be filled by new groups of organisms. For instance, in conditions of increased temperature and altered climate, sequoia-like plants may grow into giant trees with thick trunks capable of surviving in arid conditions. Scientists like Dr. Mary Higgins predict that in such conditions, new species of insects may evolve, becoming larger and more resilient to changes to fill the ecological niches previously occupied by bees and butterflies. While mammals may disappear, reptiles could take their place, evolving into larger and more social forms, similar to those that existed during the age of dinosaurs. For example, lizards and snakes could evolve into creatures capable of complex social interactions and nest building, as observed in some modern birds. In the oceans, free from human interference and pollution, coral reefs may once again flourish, forming extensive underwater structures that will serve as homes for new species of fish and invertebrates. In the face of increased ocean acidity, some types of plankton may adapt by growing larger and opening new pathways in food chains. Research indicates that these changes could lead to the emergence of unusual life forms, such as giant jellyfish that will dominate the oceans. On land, in the face of constant climate change, new mammals resembling modern elephants but smaller and adapted to hotter climates may appear. These creatures may develop long ears and a thinner layer of fat to better regulate their temperature. Additionally, in an environment devoid of humans, new predators such as large birds capable of hunting rodents may emerge, which in turn could evolve into larger and more protected forms. The change in conditions will also lead to the emergence of new forms of symbiosis, similar to those observed between termites and fungi, where new organisms will develop mutually beneficial relationships for survival. In this world, free from human activity, life will find its way to survive and adapt, creating ecosystems rich in diversity and complexity. Evolutionary specialist Dr. Stephen Lopez asserts that such changes could lead to the emergence of life forms that bear little resemblance to what we currently know. For example, organisms using bioluminescence for communication or attracting partners. It is expected that over millions of years, life on Earth will take on unexpected and astonishing forms that we can only vaguely imagine. Scientific models suggest that 10 million years after the disappearance of humans, ecosystems may become so diverse that some organisms will resemble creatures from science fiction, as we see in films and books. The Earth, as a planet, has always been in a state of change, and this will not stop. Internal processes such as plate tectonics will continue to shape continents and oceans. For instance, the process of continental drift, which began around 100 million years ago, led to the formation of the current continents, and it will not cease. As the plates move, some will collide, creating mountain ranges, while others will diverge, forming new ocean basins. Volcanic activity will also play a crucial role. Volcanoes like those in Germany, such as the Eiffel, have been active for millions of years, shaping landscapes, and this activity will continue, creating new forms of life that can adapt to changing conditions. External factors, such as solar radiation and the influence of other celestial bodies, will also affect the Earth. For example, every 100 million years, solar activity changes, which can lead to significant climate changes. This can result in periodic global warming or cooling, as it has in the past when the planet experienced ice ages. Around 100 million years ago during the Cretaceous period, dinosaurs dominated the planet, and even then, the climate could change significantly. As a result of these changes, ecosystems will evolve, creating new species. Existing ecosystems will adapt to new conditions, while some species will become extinct, as has happened in the past due to mass extinctions. For example, 5 major extinctions, including the famous one at the boundary between the Cretaceous and Paleogene periods, wiped out almost 3/4 of all species on Earth. Each of these processes will occur over billions of years, creating new diversity of life. If we consider human history, it seems like a mere instant on such vast timescales. Over the last 10,000 years, which is a tiny fraction of time in geological terms, humanity has altered the planet's landscape, but these changes are negligible compared to how the Earth has changed over billions of years. For instance, when humans began practicing agriculture, the level of carbon dioxide in the atmosphere was only 250 parts per million, whereas now it has exceeded 400 parts per million. The Earth has experienced numerous climate changes, and these changes will continue regardless of human activity. At the same time, rainfall, temperature, and sea levels will fluctuate, creating new conditions for life. Consequently, changes in ecosystems will occur constantly, creating new biomes such as tropical forests, deserts, and tundras, which will evolve and interact with each other. Over billions of years, the Earth will be able to adapt to new forms of life that may be incomparable to those that exist today. The impact of cosmic factors such as meteor showers or solar radiation will also continue to influence the Earth, possibly causing catastrophic events that will reshape the planet. For example, the impact of a meteor 65 million years ago led to the extinction of dinosaurs and paved the way for the evolution of mammals. Thus, the Earth, being in a constant state of change, will continue to evolve, and each new generation will encounter unique conditions formed under the influence of a multitude of factors. The diversity of life forms will change just as the climate, topography, and ecosystems do. As a result, the Earth will continue to adapt to changing conditions, creating new opportunities for life. The Sun, our star, is gradually becoming brighter, and this process will continue for millions of years. Scientific research indicates that every 100 million years, the Sun's brightness increases by about 1%. This means that in 5 billion years, when our star reaches the stage of a red giant, it will become significantly brighter and hotter than it is today. As a result of this increase in solar radiation, the temperature on Earth will continue to rise. Scientists predict that in a few 100 million years, the average temperature on the planet could rise to a level that is unsuitable for the existence of complex life forms. The temperature is expected to exceed 100 degrees Celsius, making the Earth's conditions extremely hostile. Oceans will begin to evaporate under the intense heat, leading to a sharp decrease in the amount of water available on the planet's surface. Around 1 billion years later, when the level of radiation becomes critically high, the biosphere will gradually retreat to the poles, where the climate will be less severe. Research shows that flora and fauna inhabiting the equatorial regions will not be able to adapt to such conditions, and most species will be subject to extinction. Only some microorganisms will be able to survive in extreme conditions, leading to a significant change in ecosystems. As the temperature continues to rise, glaciers in the Arctic and Antarctic will begin to melt, causing sea levels to rise and additional climate changes. According to calculations, oceans may completely evaporate in about 2 billion years, leaving the planet almost without water. Earth will become a desert planet where darkness and heat will reign. As a result of this process, a large part of the existing ecosystems will disappear, and the survival of complex life forms will become impossible. Such a change in climate will make Earth resemble Venus, where oxygen is almost absent, and the atmosphere consists mainly of carbon dioxide. The process of increasing the brightness of the Sun and its impact on the planet is not just hypothetical speculations, but real scientific forecasts based on the analysis of solar activity and climate changes on Earth. Ultimately, our planet will have to adapt to new conditions, and this is likely to lead to a complete change in all life forms as we know them today. Modern research shows that in 3 billion years, only the simplest organisms capable of surviving in extreme conditions will remain on Earth, and even they may face the threat of extinction. The process of weakening active plate tectonics will lead to Earth becoming a geologically dead planet. Over time, as the planet's internal heat is exhausted, convection currents in the mantle will slow down. This process will begin approximately 2 billion years from now, when the temperature in Earth's core falls below the critical threshold required to sustain magma flow. As a result, active plate boundaries, which currently cause frequent earthquakes and volcanic activity, will cease to exist. Continents that are currently in constant motion will eventually stop moving, and their motion will become so slow that it will be imperceptible to human timescales. This will lead to erosion smoothing out the landscape we know. Mountains formed over millions of years of tectonic activity will gradually erode under the influence of wind and water.
Over millions of years, mountain systems like the Himalayas will be smoothed down to a level almost indistinguishable from the surrounding plain.
Volcanic activity, which enriches the atmosphere with carbon and other elements necessary for life, will also cease. New volcanoes will not form, and old volcanoes like the Eiffel or Kilimanjaro will become dormant mountains devoid of activity. With the decrease in overall volcanic activity, the concentration of carbon dioxide in the atmosphere will drop to critically low levels, negatively impacting photosynthesis and, consequently, planetary ecosystems. Life as we know it will not be able to survive without the necessary amount of carbon and other elements that support complex ecosystems. On the planet, only primitive organisms that can adapt to new conditions will remain. Erosion will continue to act, but it will do so on already smoothed surfaces devoid of new sources of minerals and elements. Since the circulation of elements will be disrupted, Earth's ecosystems will progressively simplify and complex organisms will disappear. Ultimately, after 3 billion years, the planet will become a desolate and lifeless place, inhabited only by bacteria and simple organisms capable of surviving conditions we cannot currently imagine. At this stage, the planet will be a lifeless shell where only traces of former geological processes will remind us that life once thrived here. In 5 to 7 billion years, when the hydrogen reserves in the Sun's core are exhausted, the star will begin to transform into a red giant. At this stage, the Sun will significantly increase in size, reaching a radius that could engulf the inner planets, including Mercury and Venus. It is predicted that the Sun's maximum expansion will be around 1 million kilometers in diameter, which is 300 times its current size. This will be a result of thermonuclear reactions that will begin to occur in the envelope around the core, leading to an increase in temperature and pressure, causing the Sun to expand. On Earth, in response to this expansion, the oceans will begin to evaporate rapidly, leading to the disappearance of the entire water surface. The water that supports life will turn into water vapor, and the Earth's atmosphere will be destroyed under the intense solar radiation. Studies show that the temperature on the surface of our planet could reach critical values exceeding 1,000 degrees Celsius, making it absolutely uninhabitable. As a result of this process, which scientists call a supersun, the Earth's surface will become scorched and lifeless. Complex biological systems that we know will disappear, and the planet will plunge into chaos. The sky will be darkened by an enormous red disk of the Sun, which will occupy a large part of the visible sky, creating a spectacle that will seem to remind us of the former beauty of the planet. This phase will end when the Sun's core collapses under its own gravity, and the star will become a white dwarf, leaving behind a shell known as a planetary nebula. Modern models predict that the remnants of Earth's atmosphere will be carried into space, leaving only lifeless rocks. At this final stage, only a faint trace of the once existent life will remain, and the planet will become a cold, dead body orbiting its white dwarf. The geological heritage of Earth is a unique chronicle inscribed in the rocks and layers of sedimentary deposits, recounting the catastrophes and evolution of our planet over billions of years. Each layer of the Earth, from the oldest to the youngest, contains information about climatic changes, volcanic activity, and mass extinctions that have occurred on Earth. For instance, in geological layers formed around 660 million years ago, traces of a catastrophic event related to the impact of an asteroid have been found, which led to the extinction of dinosaurs. Scientific research shows that during this period, there was a sharp change in climate, causing mass extinction of species. Geologists studying these layers use radiometric dating methods to accurately determine the age of samples and understand the sequence of events that led to changes in ecosystems. It is as if we were flipping through the pages of a book, where each page represents a separate time interval, recording important events. For example, in layers formed due to volcanic activity, one can find minerals such as obsidian and basalt, which provide insights into the temperature and composition of magma, as well as the geodynamic processes that occurred during that period. Each layer tells its own story, and geologists, like detectives, decipher this information, creating a complete picture of the past. Scientists such as James Hutton in the 18th century began to understand that Earth is not static, but constantly changing, and his ideas about long times became the foundation for modern geological research. Layers of sedimentary rocks can be full of fossils that provide clues about which species inhabited Earth and how they evolved. For example, in layers dating back to the Triassic period, fossils of the first dinosaurs were found, which gave us an understanding of how they began to dominate the planet. Each layer, each fossil, is a testament that conveys information about past ecosystems, climatic conditions, and biological interactions. Using methods of geochemical analysis, scientists can determine the composition of the atmosphere in different historical periods, which helps restore the climatic conditions that existed in the past. In the end, Earth is a real book, whose pages are written over millions of years of evolution, each filled with unique stories about how life on the planet adapted to changes in the environment. Preserved in the rocks, evidence of catastrophes such as ice ages or mass extinctions forms a continuous chronicle that serves as a valuable resource for studying not only the history of Earth, but also for predicting future changes that may occur as a result of human activity. Scientific research continues, and each new layer discovered during geological investigations can lead to new discoveries. For example, in the 20th century, discoveries about how ocean levels and climate changed due to tectonic movements changed our understanding of the interaction between geological processes and the biosphere. Each of these aspects underscores the need for further study of the geological heritage to better understand how the past shapes our present and future. The study of ancient catastrophes requires the use of numerous methods that allow scientists to reconstruct events that occurred millions and even billions of years ago. One of the most important methods is the analysis of isotopes, which helps determine the changes that occurred in the atmosphere and oceans as a result of catastrophic events. For example, by measuring the ratio of carbon isotopes, scientists can determine the changes in the carbon cycle that occurred due to mass extinctions. Research conducted in the 2000s by a group of scientists led by Dr. James Costello showed that a sharp change in the ratio of carbon in the atmosphere around 65 million years ago corresponded to the impact of an asteroid in the Mexican Gulf, which led to the extinction of dinosaurs. Paleontological data play no less important a role. Fossil remains found in sedimentary layers provide information about which species existed and how they went extinct. For example, the analysis of trilobite remains from the Cambrian explosion period revealed how the rapid development of life on Earth was linked to changes in climatic conditions and the level of oxygen in the oceans. Geophysical research, such as seismic profiling and magnetic surveys, helps to detect traces of ancient tectonic processes and catastrophes. Scientists use these data to build models that demonstrate how tectonic movements shaped the relief and altered ecosystems. In 2010, a team of geophysicists led by Dr. Mario Taglia discovered that underwater faults in the Pacific Ocean were responsible for devastating tsunamis that changed the coastline of entire regions. Modern technologies, such as computer modeling and satellite imagery, allow us to look even deeper into the past of the planet. For example, using GIS technologies, researchers can reconstruct ancient ecosystems and assess the consequences of climate changes. In the 2000s, a project led by Dr. Emily Brown used satellite data to analyze changes in the ice sheets of Antarctica, which allowed for predicting sea level rise over the next few hundred years. These methods, when combined, create a complete picture of catastrophes, allowing scientists not only to reconstruct the past, but also to make predictions about the future of Earth. For example, the analysis of data on the extinction of species on Earth shows that current climate changes may lead to the loss of more than half of all animal and plant species by the end of the 21st century. Studying geological catastrophes is not just about investigating events that occurred millions of years ago, but also a crucial tool for understanding contemporary processes on Earth. For instance, in 2012, a group of scientists led by Dr. John Martin from the University of California, Berkeley, conducted a study using data on the largest volcanic eruptions in history, such as eruption of the Toba volcano approximately 75,000 years ago. This eruption led to global cooling and a reduction in human population. By analyzing samples of ash and gases emitted during the catastrophe, scientists were able to assess how such events could impact climate today. It was found that even relatively small eruptions can cause significant temperature changes on the planet, which are directly linked to current climate changes caused by human activity. Geologists also study earthquakes, such as the 1933 Tokyo earthquake, which destroyed part of the city and claimed the lives of more than 100,000 people. Research on tectonic plates and earthquake mechanics allows for predicting the likelihood of their recurrence, which is extremely important for countries located on the borders of plates, such as Japan and Chile. In 2019, scientists from the Japanese Meteorological Agency published a report describing earthquake models and their potential consequences based on previous catastrophes. These data help not only predict where the next earthquake might occur, but also prepare the population for possible consequences. The analysis of geological catastrophes also sheds light on ecosystem changes. For example, studying extinctions caused by large meteorite impacts, such as the one that led to the extinction of dinosaurs around 66 million years ago, helps understand how ecosystems recover from catastrophes and which species may be most vulnerable. In 2017, a study conducted by an international group of scientists showed that the speed of ecosystem recovery after a catastrophe depends on the presence of certain species that are highly resistant to environmental changes. This knowledge can help develop strategies for preserving biodiversity in the face of climate change. No contemporary natural phenomenon occurs in a vacuum. Each has its roots in the past. Scientists use old maps and data on climate changes collected over the past few thousand years to understand how past catastrophes have shaped the modern landscape and living conditions on the planet. For example, a study conducted in 2012 in Greenland showed that rapid temperature changes in the past led to massive ice melt, which in turn affects sea levels. These data allow for predicting how quickly sea levels might rise if current temperatures continue to rise. Knowledge of geological catastrophes not only enriches our understanding of Earth's history, but also underscores the importance of humility before the power of nature. Scientists like Dr. Katie Hales from the University of Melbourne emphasize that understanding Earth's history allows not only to adapt to current challenges, but also to improve preparedness for future catastrophes. In 2020, she published an article highlighting the need to integrate historical data into contemporary models for predicting natural disasters. This allows not only to improve forecasting, but also to develop effective strategies for minimizing damage. For example, using historical data on the frequency of floods in certain regions helps governments develop plans for evacuating populations and strengthening infrastructure. Research shows that knowledge of the past not only enriches our scientific base, but also serves as a vital tool for planning a sustainable future. Understanding geological catastrophes fundamentally alters our perception of human life and our place in the universe. Earth has witnessed numerous catastrophic events, such as mass extinctions, volcanic eruptions, and asteroid impacts. For instance, 300 million years ago, at the end of the Permian period, one of the most significant mass extinctions in history occurred when around 95% of all life forms disappeared. This event, known as the Permian extinction, has sparked discussions about how random catastrophes can destroy entire ecosystems and drive evolutionary changes. The recovery of life after such catastrophes requires millions of years, underscoring the fragility of existence. Scientific research indicates that such events have contributed to the evolution of new species, as only the most adaptable organisms survived. This prompts us to consider how random and unpredictable the process of evolution is. In this context, philosophers like Alfred North Whitehead argued that catastrophes serve not only as destructive forces but also as catalysts for change. Their impact on the development of life underscores that progress is not always linear and predictable, but often depends on random circumstances. Recognizing that human existence is just one episode in the long history of Earth makes us rethink our significance. Every time we observe natural catastrophes, whether they are earthquakes, floods, or volcanic eruptions, we confront the reality that our civilization may be temporary. 86 million years ago, for example, during the Cretaceous period, a second mass extinction occurred when dinosaurs disappeared, paving the way for mammals and ultimately humans. This cycle of destruction and recovery, repeated over millions of years, highlights not only the vulnerability of life but also the necessity of adaptation. We must acknowledge that each of our achievements can be threatened by sudden natural forces, raising questions about our ability to survive and progress. For example, in the 20th century, numerous natural disasters occurred, such as Hurricane Katrina in 2005, which taught us the importance of preparedness and resilience. These events demonstrate that humanity must consider not only its achievements, but also the potential threats posed by nature. Thus, our history is inextricably linked to changes on the planet, and understanding this connection helps us better understand our place in the world. Awareness of the unpredictability and fragility of life can motivate us to adopt a more responsible attitude towards our environment and ourselves. Scientific data shows that global climate change can lead to catastrophic consequences in the future, necessitating a change in our behavior. In such a context, knowledge of the past becomes a key tool for understanding how we can address the challenges of the future, which will be no less severe than those faced by our ancestors. Changes on Earth have always been an integral part of its history, and disasters that seem to be only destruction have actually served as catalysts for evolution and renewal. An example of this is an event that occurred around 65 million years ago, when an asteroid fell in the area of the current Yucatan Peninsula in Mexico, leading to mass extinction and the disappearance of dinosaurs. This extinction opened up new ecological niches for mammals, allowing them to develop and take a dominant position in ecosystems. In the geological history of Earth, we can observe how such catastrophes, such as volcanic eruptions, led to significant changes in climate, which in turn facilitated the emergence of new species. For example, around 12 million years ago, after a series of large volcanic eruptions, a sharp climate shift occurred, which opened up space for the appearance of ancestors of modern humans, such as Australopithecus afarensis. The destruction of old ecosystems creates conditions for new evolutionary experiments, allowing nature to adapt to new conditions. Such events as the Permian extinction, when around 95% of all species on Earth disappeared, created an opportunity for the flourishing of new forms of life, such as dinosaurs and, ultimately, mammals. In this chaos, a new order is born. As a result of changes, species appear that would never have emerged if the old forms of life had continued to exist. This is a cyclical process that has continued for billions of years. Each end, each catastrophe, becomes the beginning of a new stage in the history of Earth. Our planet, with its constantly changing landscapes and ecosystems, demonstrates how life finds a way to adapt and thrive, even in the most challenging conditions. These transformation processes do not stop, and each new level of evolution brings with it unique opportunities and challenges. In conclusion, consider how the history of Earth is full of paradoxes, where destruction and rebirth go hand in hand. Good night, and may the images of ancient catastrophes and rebirths in your dreams combine with your own visions, creating new, amazing worlds. From time to time, when you look at the night sky, remember that each star in it is also a testament to the endless processes of transformation that continue today. For example, the star Sirius, the closest to Earth, is 8.5 light years away and probably has already exhausted its hydrogen reserves, preparing for a future explosion.